What if I told you that the most extraordinary oceans in our cosmic neighborhood aren't on Earth at all? Could you imagine vast seas hidden where no human eye has ever seen, beneath miles of ice, on distant frozen moons? Far from our sun's warmth, beneath crusts of ancient ice, hidden oceans stir, silent, pressurized, waiting. They flow beneath the icy shells of moons orbiting giant planets, worlds that shimmer not with sunlight, but with the glow of possibility. Some span entire moons, deeper than any ocean on Earth. Others pulse with geothermal energy, creating environments that might harbor life. Tonight, we dive into the unseen waters of the cosmos. We'll journey to Europa with its spiderweb cracks, to Enceladus with its erupting geysers of salty water, to Titan with its strange methane lakes above and water oceans below. These hidden seas remind us that even in the deepest cold of space, warmth can survive. Even in darkness, life might find a way. Let your mind drift now as we explore the last great unexplored oceans of our solar system, not on our world, but worlds beyond. For most of human history, we imagined the worlds beyond Earth as barren, frozen rocks. When astronomers gazed at the moons of Jupiter and Saturn through early telescopes, they saw only distant, silent spheres, cold, lifeless, static. The very idea that liquid water could exist so far from the sun's warmth seemed impossible. Water was Earth's domain, we thought. Water was what made our planet special. How wrong we were. The journey to discovering oceans beyond Earth began slowly. In the 1970s, scientists studying Jupiter's magnetic field noticed something strange about the moon Europa. The magnetic field around this moon fluctuated in unexpected ways, suggesting something electrically conductive lay beneath its surface. Water, specifically salty water, conducts electricity. Could there be an ocean hidden under Europa's icy crust? The Voyager missions gave us our first close glimpses of these distant moons, revealing surfaces far more complex than anyone had imagined. Europa wasn't just a ball of ice. Surface was crisscrossed with cracks and ridges, like a frozen sea that had been broken apart and refrozen countless times. Ganymede showed similar features. Something was causing these ice crusts to fracture and reform. But it was the Galileo mission in the 1990s that truly revolutionized our understanding. As it orbited Jupiter, it sent back data that strongly suggested liquid water oceans beneath the icy crusts of not just Europa, but Ganymede and Callisto as well. 3 ocean worlds orbiting a single planet. The evidence was compelling magnetic signatures that could only be explained by electrically conductive liquid layers beneath the surface. Meanwhile, around Saturn, the Cassini spacecraft was making equally startling discoveries. In 2005, it captured images of something extraordinary: plumes of water vapor erupting from the south pole of a tiny moon called Enceladus. Here was direct evidence of liquid water, not just inferred from magnetic readings, but actually spraying into space. Later analysis would reveal this water contained salt and organic molecules. The implications were staggering. Think about what this means. For centuries, we thought Earth was unique in having oceans of liquid water. Now we know that ocean worlds might be common in our solar system alone. Europa, Ganymede, Callisto, Enceladus, Titan, and possibly even distant Pluto may all harbor liquid water beneath their surfaces. Each of these oceans contains more water than all of Earth's oceans combined, hidden, waiting, perhaps even teeming with life. How could liquid water exist so far from the sun? The answer lies in forces we rarely consider on Earth. Tidal heating, the stretching and squeezing of these moons as they orbit their massive parent planets, generates tremendous heat in their cores. This heat, trapped beneath insulating layers of ice, keeps water in its liquid state even in the freezing outer reaches of our solar system. It's as if these worlds have found their own internal suns, sources of energy independent from the distant star that rules our system. The realization that oceans might be common beyond Earth has profound implications for our search for life. For decades, astrobiologists focused on the habitable zone, around stars the narrow band, where a planet's surface temperature allows for liquid water. But these hidden oceans exist far outside that zone, protected from the cold vacuum of space by kilometers of ice. They challenge our understanding of where life might exist and what forms it might take. Consider Europa. Its ocean may contain twice as much water as all of Earth's oceans combined, heated from below by the Moon's core and protected from radiation by its icy shell. The ocean floor likely features hydrothermal vents, similar to those that support thriving ecosystems in Earth's deepest oceanic trenches, places where life exists without sunlight, drawing energy instead from chemical reactions. If life can thrive in such conditions on Earth, could it not do the same on Europa? Enceladus presents an even more tantalizing prospect. Its plumes have been analyzed and found to contain not just water and salt, but complex organic molecules, the building blocks of life as we know it. The Cassini spacecraft even flew through these plumes, sampling them directly. What's more, analysis of the Moon's slight wobble as it orbits Saturn suggests its ocean isn't local but global, extending beneath the entire icy crust. As our instruments became more sophisticated, more evidence accumulated. Hubble Space Telescope observations in 2016 captured what appeared to be water plumes, also erupting from Europa, suggesting its ocean too might sometimes breach its icy shell. The New Horizons mission to Pluto revealed a surprisingly young, geologically active surface features difficult to explain without the presence of a subsurface ocean keeping the crust malleable. The hunt for these hidden oceans has transformed how we think about our solar system. When I was a child, textbooks showed 9 planets circling the Sun, with Earth alone blessed with oceans and life. Today, we know our solar system contains not just one ocean world, but potentially many with more water than Earth, each with the potential for life. This revelation has shifted the focus of our space exploration. NASA's Europa Clipper mission, scheduled to launch in the coming years, will conduct dozens of close flybys of Europa, using ice-penetrating radar to map the ocean beneath and studying any plume activity it might detect. The European Space Agency's JUICE mission Jupiter, Icy Moons Explorer will study Ganymede, Callisto, and Europa, focusing on their internal oceans and potential habitability. Looking even further ahead, scientists dream of sending submarines to these alien oceans. Imagine a probe melting through kilometers of European ice, descending through the dark waters beneath, its lights illuminating an environment untouched by sunlight for billions of years. What might it find? Microorganisms floating in the currents? Complex ecosystems around hydrothermal vents? Or perhaps nothing at all, oceans, as lifeless as they are vast? The technical challenges are immense. These moons orbit deep in the radiation belts of their parent planets. Their surfaces are frigid beyond imagination, reaching temperatures of -160 degrees Celsius. The ice crusts that protect their oceans also shield them from our prying instruments, requiring new technologies to penetrate. Yet the allure of these hidden oceans is irresistible. They represent the largest unexplored environments in our solar system. They challenge our understanding of where life might exist and what forms it might take. They remind us that even after centuries of astronomy, our cosmic neighborhood still holds profound mysteries. Perhaps most importantly, they've expanded our sense of possibility. If ocean worlds are common in our solar system, might they not be common throughout the galaxy? Might not the moons of distant exoplanets harbor similar secrets? The universe may be far wetter than we ever imagined, filled with hidden seas waiting to be discovered. As we prepare for this new era of exploration, we find ourselves returning to questions that have haunted humanity since we first gazed at the night sky. Are we alone in the cosmos? Is life common or rare? What forms might it take beyond Earth? The hidden oceans of our solar system may hold the answers if only we can reach them. The search continues. With each mission, with each new piece of data, we come closer to understanding these distant seas. We map their extents, analyze their compositions, and dream of one day touching their waters. The ocean worlds beckon, their secrets protected by distance, radiation, and ice. But human curiosity is relentless, and these hidden oceans may be the greatest discovery awaiting us in our cosmic backyard. Perhaps no moon in our solar system has captured the imagination of scientists and science fiction writers alike, quite like Europa. This distant world, slightly smaller than Earth's moon, orbits the mighty Jupiter every 3.5 Earth days. From a distance, Europa presents a striking appearance: smooth, bright surface crisscrossed with dark lines, like a cracked marble or a shattered eggshell. Those lines tell a story of an ocean that refuses to stay hidden. When the Voyager spacecraft first gave us detailed images of Europa in 1979, scientists were immediately struck by how young and smooth its surface appeared. Unlike our moon with its ancient, cratered face, Europa showed few impact craters. Something was erasing them, renewing the surface. The network of linesome, straight as arrows, others curved and complex, suggested the surface was being continually reshaped. But how? The answer, scientists realized, lay in the powerful gravitational relationship between Europa and Jupiter. Europa is caught in a gravitational dance not just with Jupiter, but with its neighboring moons Io and Ganymede. This celestial ballet creates what scientists call tidal flexing. As Europa orbits, Jupiter's immense gravitational pull stretches and squeezes the moon. Imagine a rubber ball being repeatedly compressed, it would warm up. The same happens to Europa, generating heat deep in its interior. This heat is Europa's life force. It keeps what would otherwise be a frozen world alive with energy and, most importantly, maintains a vast liquid water ocean beneath its icy crust. The ice shell itself is estimated to be between 15 to 25 kilometers thicker, substantial barrier, but thin compared to the ocean beneath, which may reach depths of 100 kilometers or more. To put that in perspective, Earth's deepest ocean trench, the Mariana Trench, reaches only about 11 kilometers in depth. The cracks we see on Europa's surface tell the story of this hidden ocean. As Jupiter pulls on Europa, the ice shell flexes and fractures. Water from below can push up through these fractures, freezing when it reaches the surface and creating the dark lines visible from space. These features, called lineae, can stretch for thousands of kilometers across the moon's surface. Some appear to have shifted relative to each other, suggesting the entire ice shell is disconnected from the rocky core below, floating on a global liquid water ocean. In regions where multiple fractures intersect, we find what scientists call chaos terrain, areas where the orderly pattern of cracks gives way to jumbled, broken ice blocks that appear to have shifted, rotated, and refrozen. It's as if someone took a frozen pond, broke it into pieces, stirred it around, and let it refreeze. These chaotic regions may be places where the ice shell is thinnest, where the ocean below has most recently interacted with the surface above. Adding to the evidence for Europa's ocean was the discovery of induced magnetic fields. As Europa passes through Jupiter's powerful magnetic field, something inside the moon reacts, creating its own secondary magnetic field. The strength and behavior of this induced field match perfectly with what we would expect from a large, salty ocean. Not just any water, but salty water and electrically conductive brine similar in many ways to Earth's oceans. The Galileo mission, which orbited Jupiter from 1995 to 2003, provided even more compelling evidence. Close flybys of Europa revealed details of the surface features that strongly suggested a liquid layer beneath. The mission's magnetometer confirmed the presence of an induced magnetic field consistent with a salty ocean. By the end of the Galileo mission, the scientific consensus was clear: Europa harbors a global subsurface ocean. But perhaps the most exciting discovery came in 2012, when the Hubble Space Telescope observed what appeared to be water vapor plumes erupting from Europa's south polar region. These plumes, rising to heights of about 160 kilometers, suggest that Europa's ocean isn't always trapped beneath the ice. Sometimes, it finds ways to breach the surface, spraying into space in spectacular eruptions. While the plumes appear to be transient, they're not always visible when we look. Their very existence means we might be able to sample Europa's ocean without having to drill through kilometers of ice. What caused these plumes? Scientists believe they may be tied to the same tidal forces that keep the ocean liquid. When Europa is farthest from Jupiter in its slightly elliptical orbit, the ice shell experiences less pressure, potentially allowing water from below to push through cracks and erupt as plumes. This is similar to what we see on Saturn's moon Enceladus, though Europa's plumes appear to be less regular and predictable. The composition of Europa's ocean is a subject of intense scientific interest. Based on spectroscopic observations, the surface ice contains various compounds beyond pure water ice. There's evidence of sulfur compounds, likely originating from its neighboring moon Io, the most volcanically active body in the solar system, which constantly spews sulfur into space. There are also magnesium salts, sodium chloride, common table salt, and possibly even organic compounds. These compounds tell us something crucial about Europa's ocean. It's not just water, it's a chemically rich solution that interacts with the Moon's rocky core. On Earth, the chemistry of our oceans is largely determined by their interactions with the sea floor, particularly at hydrothermal vents, where seawater percolates through hot rocks. Similar processes likely occur on Europa, creating a chemically dynamic environment. The depth of Europa's ocean is staggering to contemplate. Estimates suggest it contains 2 to 3 times the volume of all Earth's oceans combined, despite Europa being a smaller world. This is because Europa's ocean likely encompasses the entire Moon, forming a continuous layer between the ice shell and the rocky core. On Earth, continents break up our oceans, but Europa's ocean is truly global. At the floor of this vast ocean lies Europa's rocky core. Models suggest this core is likely hot and geologically active, heated by the same tidal forces that keep the ocean liquid. The boundary between this warm core and the ocean above would be a zone of intense chemical activity. On Earth, similar boundaries at deep-sea hydrothermal vents support rich ecosystems completely independent of sunlight, deriving energy instead from chemical reactions. Could similar ecosystems exist in Europa's dark waters? The ingredients seem to be present: liquid water, essential chemical elements, and a source of energy. Life on Earth has shown remarkable adaptability, flourishing in environments once considered too extreme for biology. The crushing pressures of deep ocean trenches, the searing heat of hydrothermal vents, the freezing temperatures of Antarctic ice. Europa's ocean, while alien, might not be too extreme for life to evolve and thrive. The ice shell itself may also be more complex than initially thought. Rather than a uniform layer of solid ice, it might include lens-shaped pockets of liquid water lakes suspended within the ice shell. The chaos regions on the surface could be places where such lakes have interacted with the surface. These lakes might provide habitats distinct from the main ocean below, perhaps with different chemical compositions and energy sources. Europa's surface is bathed in intense radiation from Jupiter's magnetosphere, which traps and accelerates charged particles from the solar wind. This radiation is destructive to most forms of life as we know it, making the surface itself highly inhospitable. However, it also creates an interesting chemical environment. The radiation breaks apart water molecules and other compounds, creating oxidants chemicals that could potentially serve as energy sources for life if transported down to the ocean below. This creates a tantalizing possibility Europa might have not only the ingredients for life but also an energy cycle to sustain it. Oxidants created at the surface could be carried down to the ocean through cracks or subduction of ice plates, where they could react with reagents coming from the ocean floor, releasing energy that life could harness. It's a cycle reminiscent of Earth's, where surface processes and deep-sea chemistry create the energy gradients that power our biosphere. The movement of ice on Europa's surface provides clues about the dynamics of the hidden ocean. Some of the linear features show lateral displacement, like the transform faults of Earth's tectonic plates. These suggest that blocks of ice are moving relative to each other, perhaps driven by convection in the ocean below or by the flow of warm ice at the base of the ice shell. Europa may have its own version of plate tectonics, with ice rather than rock as the medium. Another fascinating feature of Europa's surface is its color. While predominantly bright white, reflecting much of the sunlight that hits it, it also shows patches of reddish-brown material, particularly along the cracks and in the chaos regions. This coloration is believed to come from salts and other compounds that have been exposed to Jupiter's intense radiation, altering their molecular structure and creating what scientists call irradiated salts. The specific compounds responsible might include magnesium sulfate, sodium sulfate, and even sodium chloride that has been radiation damaged. These colorful compounds give us indirect clues about the ocean's chemistry. If confirmed to be salts, they suggest an ocean that has been in prolonged contact with a rocky seafloor, leaching out minerals and becoming increasingly briny over time. The presence of chlorides, in particular, would make Europa's ocean even more Earth-like in its basic chemistry. Europa's place in Jupiter's system also affects its potential for habitability. It orbits between the volcanic moon Io and the massive moon Ganymede. This position subjects it to radiation from Jupiter and material ejected from Io, while also stabilizing its orbit through gravitational resonances with Ganymede. This orbital resonance is crucial. It helps maintain the elliptical shape of Europa's orbit, which in turn maximizes the tidal flexing that keeps its ocean liquid. Europa completes one rotation on its axis in the same time it takes to orbit Jupiter, what astronomers call a synchronous rotation. This means the same side of Europa always faces Jupiter, just as the same side of our Moon always faces Earth. But unlike our Moon, Europa's orbit is slightly elliptical, which means Jupiter appears to wobble slightly in Europa's sky. This wobble, combined with the varying gravitational forces as Europa moves closer to and farther from Jupiter, contributes to the complex pattern of stresses in its ice shell. At Europa's surface, temperatures are brutally cold, averaging about -160 degrees Celsius. At these temperatures, ice behaves like rock, brittle and hard. But deeper in the shell, where temperatures are warmer, ice can flow like a very slow-moving liquid, similar to how glaciers flow on Earth. This creates a complex ice shell with different mechanical properties at different depths. The boundary between the ice shell and the liquid ocean below is a particularly interesting zone. Here, the base of the ice shell may consist of partially frozen, slushy ice rather than a sharp boundary. This slushy layer might provide a habitat for microbial life, similar to how organisms on Earth can survive within the brine channels of sea ice in polar regions. As we contemplate sending missions to explore Europa more closely, one of the biggest questions is how thick the ice shell really is. If we hope to one day sample the ocean directly, the thickness of the ice presents a formidable challenge. Estimates range from as little as 10 kilometers to as much as 30 kilometers, with the most recent analysis suggesting the lower end of that range might be more accurate, at least in some regions. NASA's upcoming Europa Clipper mission, scheduled to launch in 2024 and arrive at Jupiter several years later, aims to help answer this question. Equipped with ice-penetrating radar, it will attempt to measure the thickness of the ice shell and possibly detect lakes within it. It will also carry instruments to analyze the composition of the surface, study any plume activity, and further characterize the magnetic field to better understand the ocean's depth and salinity. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, will also study Europa, though its primary target is Ganymede. Together, these missions will give us our closest look yet at Europa and help determine the next steps in exploring this ocean world. The ultimate goal, of course, would be to one day breach the ice shell and sample Europa's ocean directly. Concepts for such missions range from nuclear-powered melting probes that would slowly melt their way through the ice, to impactors that would create debris plumes for analysis by an orbiting spacecraft, to landers that would sample potential freshly exposed ocean material at the surface. Each approach presents enormous technical challenges. The radiation environment around Europa damages electronics, requiring substantial shielding. The extreme cold makes power generation difficult and limits the functionality of many mechanical systems. The distance from Earth means communications are delayed by tens of minutes, requiring spacecraft to operate autonomously. Despite these challenges, the scientific payoff would be immense. Directly sampling and analyzing Europa's ocean would be one of the most significant achievements in the history of space exploration. If life exists there, its discovery would transform our understanding of biology and our place in the universe. Even if no life is found, understanding the chemistry and physical processes of this vast alien ocean would provide invaluable insights into planetary evolution and comparative oceanography. As we continue to study Europa from afar and plan ever more ambitious missions to explore it up close, we're reminded of how much this distant moon has already changed our perspective. Once thought to be just another lifeless, frozen rock, Europa has revealed itself to be a dynamic world with one of the most precious substances in the universe, liquid water, in greater abundance than even our blue planet Earth. Its cracked shell conceals an ocean of possibilities, including perhaps the greatest discovery awaiting humanity among the worlds of our solar system. Among Saturn's diverse family of moons, Enceladus stands as perhaps the most surprising. Small enough to fit within the borders of many countries on Earth, with a diameter of only 500 kilometers, this tiny moon has defied every expectation scientists had for a world of its size. When the Voyager spacecraft flew past in the early 1980s, they revealed a bright, icy surface, reflecting more than 90% of the sunlight that strikes it, making Enceladus the most reflective body in our solar system. But it wasn't until the Cassini mission arrived at Saturn in 2004 that this unassuming moon revealed its most extraordinary secret: is actively spraying its ocean into space. The discovery came in 2005, when Cassini's cameras captured something astonishing: plumes of material erupting from Enceladus's south polar region, extending hundreds of kilometers into space. These weren't subtle emissions, detectable only by specialized instruments. They were dramatic geysers, visible even in images taken from hundreds of thousands of kilometers away. Saturn's seemingly quiet moon was venting material into space, with enough force to escape its gravity entirely. Some of this material even contributes to Saturn's E-ring, a tenuous ring composed primarily of microscopic ice particles. What makes these plumes even more remarkable is their composition. As Cassini flew through them during carefully planned encounters, its instruments analyzed their makeup directly. The plumes consist primarily of water vapor and ice particles, but they also contain salt, suggesting they originate from a body of liquid salt water. Most intriguing of all, they contain organic compounds, carbon-based molecules that on Earth are associated with living processes. The specific compounds detected include methane, carbon dioxide, and various complex organic molecules, including some that contain nitrogen. The source of these plumes, scientists discovered, are distinctive features on Enceladus's south pole called tiger stripes. These parallel fractures, each roughly 130 kilometers long and spaced about 35 kilometers apart, are visibly warmer than the surrounding ice. They've been named after cities in the Middle East and North Africa mentioned in the tales of the Arabian Nights: Alexandria, Cairo, Baghdad, and Damascus. From these warm fractures, more than 100 individual jets of material spray outward, feeding the larger plumes visible from a distance. Why is Enceladus active when many similar-sized moons are geologically dead? Like Europa, the answer lies in orbital resonances and tidal heating. Enceladus orbits Saturn in resonance with another moon, Dione, with Enceladus completing exactly 2 orbits for every one of Dione's. This orbital dance causes Enceladus's orbit to be slightly elliptical, rather than perfectly circular. As it moves closer to and farther from Saturn during each orbit, the gas giant's gravitational pull varies, stretching and squeezing the small moon. This flexing generates friction in Enceladus's interior, which in turn creates enough heat to maintain liquid water when the moon should, by all rights, be frozen solid at its distance from the sun. The heat isn't distributed evenly throughout Enceladus. It's concentrated at the south pole, creating what scientists call a thermal anomaly. The south polar region shows surface temperatures as high as -180 degrees Celsius, still incredibly cold by Earth standards, but substantially warmer than the rest of the moon, which can reach temperatures below -240 degrees Celsius. This concentrated heating at the South Pole is a puzzle in itself, possibly related to a thinner ice shell in that region, or to the specific way tidal forces act on Enceladus's interior structure. The plumes vary in intensity over time, appearing stronger when Enceladus is farther from Saturn in its elliptical orbit. This makes sense from a physical perspective. When the moon is farther from Saturn, there's less gravitational pressure compressing the fractures shut, allowing more material to escape. The cyclical nature of the plume activity provides additional evidence that they're tied to tidal forces. Beyond the visual confirmation of the plumes, one of the most compelling pieces of evidence for a subsurface ocean came from Cassini's measurements of Enceladus's slight wobble as it orbits Saturn. This wobble, called a libration, is larger than would be expected if the moon were solid throughout. The best explanation is that the icy crust is disconnected from the rocky core by a layer of liquid, allowing the shell to oscillate more freely. Based on these measurements, scientists estimate the ocean is about 10 kilometers deep on average, with the ice shell above varying from as thin as 2 kilometers at the South Pole to over 30 kilometers thick in other regions. The thinness of the ice at the South Pole explains why the ocean can interact with the surface there, creating the tiger stripe fractures and allowing water to escape as plumes. It's as if Enceladus has a weak spot in its armor, a place where its hidden ocean can reach the surface and reveal itself to passing spacecraft. What makes Enceladus particularly exciting for astrobiologists is that Cassini was able to directly sample its ocean by flying through the plumes. No other ocean beyond Earth has been so directly accessible to our instruments. The plumes provide a convenient sample of the ocean's chemistry, without requiring the immense technological challenge of landing and drilling through ice. It's as if Enceladus is offering us a free sample of its most interesting feature. Analysis of the plume material revealed not just water and simple organics, but complex macromolecular organic compounds with masses exceeding 200 atomic mass units. These aren't definitive biosignatures. They can be created by non-biological processes, but they are the type of complex carbon compounds that would be expected in an environment supporting life. Perhaps most exciting was the detection of molecular hydrogen in the plumes, which suggests hydrothermal activity where the ocean meets the rocky core. On Earth, hydrothermal vents at the ocean floor support rich ecosystems independent of sunlight. Microorganisms at these vents derive energy from the chemical reaction between hydrogen and carbon dioxide, a process called methanogenesis. The presence of both hydrogen and carbon dioxide in Enceladus's plumes suggests similar chemical energy sources could be available in its ocean. If life similar to Earth's deep-sea vent communities exists on Enceladus, it would have the necessary energy source to survive. The rocky core itself plays a crucial role in Enceladus's potential habitability. Estimated to be porous and permeable, it likely allows water to circulate through it, dissolving minerals and participating in chemical reactions that produce heat and release compounds into the ocean. This interaction between water and rock is crucial for life as we know it, providing essential elements and energy sources. The core's porosity might result from its formation through the accretion of smaller bodies, leaving spaces between them rather than forming a fully compacted sphere. Salt concentrations in the plumes suggest Enceladus's ocean is about as salty as Earth's oceans, containing primarily sodium chloride ordinary table salt along with sodium carbonate and potentially other compounds. This salinity indicates prolonged interaction between the ocean and the rocky core, as water dissolves minerals over geological timescales. The pH of the ocean, inferred from the plume composition, appears to be alkaline, with values estimated between 8 and 11. This alkaline environment, combined with the presence of silica nanoparticles in the plumes, provides further evidence for hydrothermal activity similar to the Lost City vent field in Earth's Atlantic Ocean, where seawater reacts with the mineral olivine in a process called serpentinization. This reaction produces hydrogen and heat, while creating a chemical environment potentially favorable for the emergence of life. Enceladus's ocean appears to be global, extending beneath the entire surface, rather than being restricted to the South Polar region. This global ocean is maintained in its liquid state primarily by tidal heating, though other heat sources may contribute. Radioactive decay in the core likely provides some background heating, and exothermic chemical reactions between water and certain minerals in the core could also generate heat. The age of the South Polar terrain is relatively young in geological terms, estimated at between 30 and 100 million years. The rest of Enceladus shows varying surface ages, with some regions bearing more impact craters, suggesting they've been exposed to space for longer periods. This indicates that Enceladus's geological activity has varied over time, perhaps with different regions becoming active and then dormant as internal dynamics shifted. One of the most remarkable aspects of Enceladus's activity is its efficiency. The total power being dissipated as heat at the South Pole is estimated at about 16 gigawatts, equivalent to the power consumption of a moderate-sized country on Earth. While this sounds substantial, it's actually a relatively modest amount of energy for a planetary body, making it all the more surprising that this small moon maintains such dramatic geological activity. This efficiency might be explained by the focused nature of the heating at the South Pole and the relatively thin ice shell in that region. The plumes themselves eject between 100 and 300 kilograms of material every second, enough to fill an Olympic swimming pool in just a few hours. Most of this material falls back to Enceladus's surface as snow, creating the pristine, reflective surface we observe. Some escapes Enceladus's weak gravity to feed Saturn's E-ring, while a small fraction is ejected with enough velocity to escape Saturn's gravity entirely, venturing into interplanetary space. The tiger stripe fractures themselves are fascinating geological features. Their parallel arrangement suggests they formed sequentially rather than simultaneously, with each new fracture forming parallel to the existing ones due to the stress patterns in the ice shell. They appear to be in constant motion, opening and closing slightly with each orbit around Saturn. This breathing motion allows the water vapor and ice particles to escape when the fractures are more open and may help prevent them from freezing shut despite the extreme cold of space. Inside these fractures, conditions are unlike anywhere else on Enceladus. The walls may be coated with fresh ice crystals, continuously deposited by condensing water vapor. Salt crystals might form where briny water droplets freeze and the water sublimates away, leaving the minerals behind. In some places, the fractures might widen into small subsurface chambers, where liquid water could exist briefly before freezing or vaporizing. The plume activity also creates a unique environment around Enceladus. The ejected water vapor and ice particles form a tenuous atmosphere or exosphere around the Moon, most dense near the South Pole. This water-rich environment extends Enceladus's influence far beyond its small physical size, interacting with Saturn's magnetic field and affecting the space weather of the entire Saturnian system. Future missions to Enceladus would likely focus on the plumes and their composition. A spacecraft, equipped with more sensitive instruments than Cassini, could analyze the organic compounds in greater detail, potentially detecting amino acids, fatty acids, or other biomolecules if they exist in the ocean. It could also better characterize the physical conditions at the Tiger Stripes, measuring temperatures with higher precision and mapping the exact locations of individual jets. The ultimate mission would be a lander that could sample the fresh material around the Tiger Stripes directly, avoiding the need to drill through kilometers of ice to access the ocean. Such a mission could analyze the chemical and potential biological content of the ocean with much greater precision than is possible during brief plume fly-throughs. It could also deploy seismometers to study the thickness of the ice shell and the dynamics of the ocean beneath more accurately. Even more ambitious would be a submarine or cryobot that could melt through the thin ice at the South Pole and explore the ocean directly. While technically challenging, the relatively thin ice in this region makes such a mission more feasible than similar concepts for Europa with its thicker ice shell. An autonomous underwater vehicle could search for hydrothermal vents at the ocean floor and directly observe any ecosystems that might exist there. The discovery of Enceladus's plumes has revolutionized our understanding of the outer solar system. Before Cassini, few would have predicted that such a small moon could maintain geological activity, much less host a potentially habitable ocean. Now, this tiny world ranks among the top targets in our search for life beyond Earth. Its combination of liquid water, organic compounds, chemical energy sources, and direct accessibility through its plumes makes it uniquely valuable for astrobiological exploration. As we contemplate the bright ice particles spraying from this distant moon, we're reminded that the solar system is far more dynamic and surprising than we once believed. Worlds that should be frozen and dead instead pulse with hidden energy. Oceans exist where no one expected to find them. And perhaps life has found a foothold in these hidden seas, beneath the icy armor of a moon less than 1/7 the diameter of our own. Enceladus teaches us humility in our expectations about where habitability is possible. Before we discovered its plumes, astrobiology focused primarily on Mars and Europa as potential habitats beyond Earth. Now, we must consider that even small, seemingly unassuming worlds might harbor the conditions for life. This broadens our search considerably, not just within our solar system, but as we contemplate the moons of giant planets around other stars as well. The ongoing analysis of Cassini's data continues to reveal new insights about Enceladus years after the mission's end. As our analytical techniques improve and our understanding of extreme environments on Earth advances, we gain new perspectives on this distant ocean world. Each discovery builds our anticipation for future missions that will continue the exploration. Cassini began, perhaps one day answering the ultimate question, does life exist in the hidden ocean of this small but remarkable moon? When Jupiter reveals itself through even a modest telescope, 4 bright points of light can be seen dancing around the giant planet. These are the Galilean moons, named after their discoverer, the Italian astronomer Galileo Galilei, who first observed them in 1610. Among these 4 worlds, Ganymede stands as the true giant larger than the planet Mercury, measuring 5,268 kilometers in diameter. If Ganymede orbited the Sun instead of Jupiter, we would undoubtedly classify it as a planet in its own right. Yet despite its impressive size, For centuries, this distant world revealed little of its true nature to astronomers peering through their telescopes. What makes Ganymede truly remarkable isn't just its size, but what lies beneath its surface. Hidden under a complex crust of ice and possibly minerals, Ganymede likely harbors the deepest ocean in our solar system, a vast body of liquid water that may contain more than all of Earth's oceans combined. This hidden sea isn't just a thin layer, but a tremendous volume that may comprise multiple distinct layers, creating a complex water world unlike anything in our immediate cosmic neighborhood. Ganymede's story began to unfold in greater detail when NASA's twin Voyager spacecraft flew past Jupiter in 1979. The images they sent back revealed a world with two distinct types of terrain: dark, heavily cratered regions that appear to be ancient, and lighter, grooved areas with fewer craters, suggesting they formed more recently. These grooved regions create intricate patterns across large portions of the surface, with parallel ridges and troughs stretching for hundreds of kilometers, giving parts of Ganymede the appearance of a grooved record or plowed field when viewed from orbit. Scientists now believe these grooved terrains formed through tectonic activity, the movement and fracturing of Ganymede's icy crust. But unlike Earth's tectonics, which are driven by our planet's internal heat and the movement of continental plates on a partially molten mantle, Ganymede's surface features were likely formed as its icy shell fractured and shifted above a hidden ocean. As the moon evolved and its internal structure changed, the ice above experienced stresses that created the complex pattern of grooves we see today. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided the first compelling evidence for Ganymede's subsurface ocean. Galileo carried a magnetometron instrument designed to measure magnetic field sand. What it discovered at Ganymede was unprecedented among moons in our solar system. Ganymede generates its own intrinsic magnetic field, similar to Earth's but much weaker. This was a stunning discovery, as generating a magnetic field typically requires a molten, electrically conductive core with fluid motions inside. But Galileo discovered something even more interesting. Superimposed on Ganymede's intrinsic magnetic field was an induced magnetic field, one that changed as Ganymede moved through Jupiter's powerful magnetosphere. This induced field is exactly what would be expected if Ganymede contained a large, electrically conductive layer beneath its surface, salty ocean. The combination of these magnetic signatures provided strong evidence that beneath Ganymede's icy crust lies a vast ocean of liquid salt water. Further observations strengthened this conclusion. The Hubble Space Telescope observed Ganymede's aurora-glowing regions in its thin atmosphere, caused by charged particles following magnetic field lines. The behavior of these auroras provided additional evidence for an electrically conductive layer beneath the surface. By 2015, scientists were confident enough to announce that Ganymede definitely hosts a subsurface ocean. What makes Ganymede's ocean particularly fascinating is its potential structure. Models based on Ganymede's density, size, and the behavior of water under extreme pressures suggest that its ocean may be arranged in layers. At the bottom, pressing against the rocky core, may be exotic forms of ice that form under immense pressure, what scientists call high-pressure ice polymorphs like Ice 6 and Ice 7. These exotic ices have crystal structures different from the ice we're familiar with on Earth and remain solid even at temperatures that would melt normal ice. Above these exotic ice layers may lie the liquid water ocean, sandwiched between two different forms of ice, the high-pressure forms below and the more familiar ice eye forming the outer crust. This creates a unique situation where Ganymede's ocean doesn't directly contact its rocky core, as Europa's and Enceladus's oceans likely do. Instead, Ganymede's ocean may be isolated from the mineral nutrients of its core by a barrier of exotic ice. This has important implications for potential habitability, as the water-rock interactions that could provide energy and nutrients for life might be limited. The total volume of water in Ganymede's ocean is staggering, estimated to be around 30 times the volume of all Earth's oceans combined. The sheer scale of this hidden sea makes it the largest known body of liquid water in our solar system. While Europa and Enceladus may have proportionally more liquid water for their size, Ganymede's greater volume makes its ocean the true titan among the solar system's hidden seas. Observations suggest the ocean may be quite deep, possibly extending to depths of 100 to 150 kilometers. The ice shell above is estimated to be around 150 kilometers thick, much thicker than the shells of Europa or Enceladus. This substantial barrier would insulate the ocean from the extreme cold of space, while the ocean itself would be kept liquid by internal heat sources and the tremendous pressure exerted by the ice above. What keeps this vast ocean liquid when Ganymede orbits so far from the Sun? Like Europa and Enceladus, tidal heating plays a role, though to a lesser extent. Ganymede is in an orbital resonance with Europa and Io, completing one orbit for every 2 of Europa's and 4 of Io's. This creates a relatively stable, nearly circular orbit that produces less dramatic tidal flexing than Europa experiences. Additionally, radioactive decay in Ganymede's rocky core provides background heating, while the thick ice shell above serves as excellent insulation, trapping heat inside. The salinity of Ganymede's ocean remains uncertain but is likely significant. The induced magnetic field suggests the water contains dissolved salts that make it electrically conductive. These might include magnesium sulfate, sodium sulfate, or sodium chlorodecimiller to the salt compositions inferred for Europa and Enceladus. This salinity would lower the freezing point of the water, helping to keep it liquid at temperatures below 0 degrees Celsius. Ganymede's rocky core is proportionally smaller than those of the other Galilean moons, making up about half its total diameter. This core likely contains silicate minerals and metals, particularly iron. The core's size and density suggest that Ganymede underwent some degree of differentiation early in its history, with denser materials sinking toward the center, while lighter materials rose toward the surface. The warming that accompanied this differentiation might have been one of the original sources of heat that melted the ice and formed the ocean. Ganymede's distinctive surface features tell a complex geological story. The dark, cratered terrain represents the oldest surface, perhaps dating back almost to the Moon's formation over 4 billion years ago. These regions bear the scars of countless impacts accumulated over eons, their darkness possibly resulting from a mixture of rocky material mixed with the ice. In contrast, the younger, lighter grooved terrain shows evidence of tectonic resurfacing, where old surface features were destroyed and replaced by the parallel grooves and ridges we see today. This grooved terrain covers about 2/3 of Ganymede's surface, and appears to have formed through extension, the stretching and thinning of the crust, as Ganymede expanded slightly. This expansion likely occurred when part of its interior water froze, since water expands as it turns to ice. As the Moon expanded, its brittle surface cracked, creating the grooved patterns. The grooves themselves may be complex systems of ridges and troughs, similar in some ways to Earth's rift valleys, but composed of ice rather than rock. Impact craters on Ganymede show unusual forms not seen on rocky worlds like Earth's moon. Many large craters have flat floors and lack the central peaks typical of impacts on rocky bodies. Some have been modified by the movement of the icy crust, appearing stretched or torn apart by tectonic forces. Others are surrounded by bright rays of ejected material, which on Ganymede likely consists of fresh, clean ice exposed by the impact and scattered across the surface. One of the most striking features on Ganymede is a large, dark, circular region called Galileo Regio, measuring about 3,200 kilometers across. This is one of the oldest portions of Ganymede's surface, heavily cratered and marked by subtle concentric rings that may have formed through ancient tectonic processes. Similar, though smaller, dark regions include Marius Regio and Perine Regio. These ancient landscapes provide windows into Ganymede's distant past. The younger, grooved terrain has been given names like Uruk Sulcus and Phrygia Sulcus, where sulcus refers to the parallel grooves that characterize these regions. These areas show fewer impact craters, suggesting they formed more recently or have been modified by geological processes that erased older craters. The boundaries between the dark, ancient terrain and the lighter, grooved regions are often sharp, indicating that tectonic forces essentially tore apart the older surface and replaced it with new material from below. Ganymede possesses an extremely thin atmosphere, or exosphere, primarily composed of oxygen. This oxygen isn't produced by life as on Earth, but rather by charged particles from Jupiter's magnetosphere striking the icy surface, breaking apart water molecules and liberating oxygen. The Moon also has polar caps, though they differ from Earth's. Rather than being composed of seasonal ice, these caps appear to be made of frost formed by water molecules migrating across Ganymede's surface and settling in the colder polar regions. What truly sets Ganymede apart from all other moons in our solar system is its magnetic field. No other moon is known to generate its own intrinsic magnetic field. The prevailing theory is that this field is generated by a metallic core that remains partially liquid, with convective motions of electrically conductive material, creating a dynamo effect similar to Earth's, though much weaker. This means Ganymede may have a layered interior with a solid inner core and liquid outer core, similar in structure to Earth but composed of different proportions of materials. This magnetic field creates a small magnetosphere within Jupiter's much larger one-year moon with its own magnetic bubble, the only known case in our solar system. When Jupiter's magnetic field points in the opposite direction to Ganymede's, the two fields connect in a process called magnetic reconnection, creating pathways for charged particles to enter Ganymede's magnetosphere and spiral along field lines toward the Moon's poles, creating the auroras observed by the Hubble Space Telescope. The magnetic field may have important implications for the ocean beneath the surface. On Earth, our magnetic field shields us from much of the charged particle radiation from the Sun. Similarly, Ganymede's magnetic field may provide some protection for its ocean from Jupiter's intense radiation environment. This could create more stable conditions for any hypothetical life that might exist there, reducing one of the stresses that such life would face. Jupiter's intense radiation belts create challenging conditions at Ganymede. The trailing hemisphere, which faces backward along Ganymede's orbit, receives more intense radiation than the leading hemisphere. This radiation affects the chemistry of the surface ice, potentially creating compounds that give different regions their distinct colors. It may also help explain why Ganymede's surface appears generally brighter than that of its neighbor Callisto, which orbits farther from Jupiter in a less intense radiation environment. The Juno mission, which has been orbiting Jupiter since 2016, has provided new insights into Ganymede. In June 2021, Juno conducted a close flyby of Ganymede, passing within 1,038 kilometers of its surface, the closest any spacecraft had come to the Moon since Galileo's final flyby in 2000. Juno's instruments captured high-resolution images of the surface and gathered data about its composition and interaction with Jupiter's magnetic field, contributing to our evolving understanding of this complex world. Looking ahead, Ganymede will be a prime target for the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, scheduled to launch in 2023. JUICE will conduct multiple flybys of Ganymede before eventually entering orbit around the Moon in 2034, becoming the first spacecraft to orbit a moon other than Earth's. Its suite of instruments will study Ganymede's interior structure, surface composition, and magnetic field in unprecedented detail, potentially revolutionizing our understanding of this ocean world. Could Ganymede's ocean harbor life? The question is more complex than for Europa or Enceladus. The ocean's suspected separation from the rocky core by layers of high-pressure ice might limit the water-rock interactions that could provide chemical energy for life. However, the interface between the ocean and the ice layers above and below would create interesting chemical and thermal gradients that could potentially be exploited by living organisms. Life as we know it requires liquid water, essential chemical elements, and an energy source. Ganymede provides the first requirement in abundance, and the chemical elements are likely present in its ocean. The energy sources are less certain with reduced tidal heating compared to Europa and potential isolation from core materials. The available energy for life might be more limited. However, radiation at the surface could produce oxidants that, if transported to the ocean below, could provide chemical energy through reactions with reductants. Any life in Ganymede's ocean would need to be adapted to conditions quite different from most of Earth's biosphere. The pressure at the bottom of the ocean would be extreme, though not beyond the range that some terrestrial deep-sea organisms can tolerate. Temperatures would be cold, but likely above freezing throughout much of the ocean. The chemical composition, while not yet well constrained, would probably include salts and possibly other compounds that would create a challenging but not necessarily inhospitable environment. One intriguing possibility is that life could exist at the boundaries between liquid water and ice. On Earth, organisms have been found living in brine channels within sea ice. Similar niches might exist at the upper boundary of Ganymede's ocean, where the liquid water meets the ice shell. Even more exotic would be potential habitats at the lower boundary, where liquid water interfaces with high-pressure ice, forms not commonly found on Earth. The age of Ganymede's ocean is another factor relevant to its potential habitability. If the ocean has existed in roughly its current form for billions of years, as some models suggest, it would have provided a stable environment over geological timescales, potentially long enough for life to emerge and evolve. Alternatively, if the ocean's structure has changed significantly over time, perhaps transitioning between different ice configurations, this could have created challenges for any emerging biosphere. Exploring Ganymede presents unique challenges. Its thick ice shell makes direct access to the ocean more difficult than at Europa or Enceladus. Unlike Europa, which likely has regions where the ice is relatively thin, and Enceladus, which conveniently sprays its ocean into space through the south polar plumes, Ganymede keeps its ocean well isolated. Any mission seeking to sample this ocean would need to penetrate much deeper than on the other ocean moons. However, Ganymede also offers certain advantages for exploration. Its distance from Jupiter places it in a less intense radiation environment than Europa, potentially extending the operational lifetime of spacecraft. Its size makes it easier to establish a stable orbit around it, and its intrinsic magnetic field could provide interesting opportunities to study how a small planetary body generates and maintains such a field, offering comparisons with Earth's much stronger field. As we contemplate the depths of Ganymede's ocean, we're struck by the contrast between what we can see and what remains hidden. From Earth, or even from spacecraft like Juno passing nearby, Ganymede appears as a silent, icy world marked by ancient scars and mysterious grooves. Yet beneath this quiet exterior may lie the largest ocean in our solar system, a vast, dark realm where pressure increases with depth until water itself takes on exotic forms unknown on Earth's surface. If we could descend through this ocean, what would we find? Near the top, where the water meets the ice shell, temperatures would be coldest, perhaps just above freezing. As we descended, the pressure would increase dramatically, while the temperature might rise slightly due to heat from below. Eventually, we would reach depths where the pressure transforms liquid water into exotic ice, even though the temperature remains above the normal freezing point. These high-pressure ice forms create a boundary that might separate the ocean from the rocky core below, creating a water world sandwiched between different types of ice. Ganymede teaches us that looks can be deceiving. What appears as a quiet, relatively unchanged moon harbors dynamic processes beneath its surface. Its magnetic field reveals a molten core still active after billions of years. Its grooved terrain tells of geological upheavals that reshaped vast portions of its surface. And its hidden ocean speaks to the possibility that habitable environments might exist in places we once thought lifeless. In studying Ganymede, we're reminded once again that the solar system holds wonders we're only beginning to understand, and perhaps life in forms we're only beginning to imagine. Among Jupiter's family of large moons, Callisto stands as something of an outlier. While its siblings Io, Europa, and Ganymede show clear signs of intense geological activity, past or present, Callisto presents a different face to the cosmos. Its surface is ancient and scarred, bearing the impact craters of billions of years without significant renewal. If the other Galilean moons tell stories of dynamic change, Callisto whispers tales of preservation and patience. Yet beneath its weathered exterior, this seemingly dormant world may harbor a secret of its own, a hidden ocean of liquid water, quietly persisting through the eons. Callisto is the second largest of Jupiter's moons and the third largest moon in our solar system, measuring 4,820 kilometers in diameter. It orbits farther from Jupiter than the other Galilean moons, completing one revolution every 16.7 Earth days. This greater distance from Jupiter's gravitational influence has profound implications for Callisto's evolution and character. While its closer siblings experience intense tidal heating that drives their geological activity, Callisto's more distant orbit results in much less internal heating. The consequence is a world that appears to have changed little since the early days of our solar system. When the Voyager spacecraft captured images of Callisto in 1979, they revealed a surface unlike any other in the Jovian system. Nearly every square kilometer bears the marks of impacts, from large craters dozens of kilometers across to minute pits, barely visible even in high-resolution images. This makes Callisto's surface one of the most heavily cratered in the entire solar system, a testament to its great age. Scientists estimate that some regions of Callisto's surface are over 4 billion years old, dating back to the period known as the Late Heavy Bombardment, when impacts were frequent throughout the solar system. The most striking feature on Callisto is Valhalla, an enormous impact basin measuring over 3,000 kilometers across nearly the size of the continental United States. Unlike impact basins on rocky worlds like our moon, Valhalla doesn't appear as a deep depression, but rather as a system of concentric rings, like ripples in a pond, spreading outward from a relatively small central bright region. This unusual morphology results from impacts into a surface that, while rigid, has some capacity to flow and adjust over geological timescales consistent with a crust composed primarily of ice rather than rock. Other large multi-ring impact structures dot Callisto's surface, including Asgard, measuring about 1,600 kilometers across, and Adlinda, a mere 1,000 kilometers in diameter. These features, along with countless smaller craters, give Callisto a uniformly rough appearance. Unlike Europa and Ganymede, Callisto shows no evidence of the grooved terrain that suggests active tectonics. There are no signs of volcanic activity as on Io, no fractures as on Europa, and no regions of relatively recent resurfacing as on Ganymede. This apparent inactivity led many scientists to initially consider Callisto a completely frozen world, perhaps solid ice and rock throughout. However, data from NASA's Galileo mission in the 1990s hinted at a more complex reality. Like Europa and Ganymede, Callisto showed evidence of an induced magnetic field when passing through different parts of Jupiter's magnetosphere. This suggested the presence of an electrically conductive layer beneath the surface, most likely a salty liquid water ocean. If this interpretation is correct, Callisto joins its siblings as another ocean world in the Jovian system. However, its ocean would be fundamentally different in character from those of Europa and Ganymede. Rather than being heated primarily by tidal forces, Callisto's ocean would be maintained by the residual heat of the moon's formation and radioactive decay in its rocky components. Combined with the insulating effect of the thick ice shell above, it would be a quieter, perhaps colder ocean, less energetic than those of its neighbors, but potentially no less interesting. The depth of this ocean and the thickness of the ice shell above it remain subjects of ongoing research. Models suggest the ocean might begin about 150 to 200 kilometers beneath the surface and extend to depths of up to 250 kilometers. This would place it significantly deeper than Europa's ocean, but possibly comparable to Ganymede's in terms of distance from the surface. Unlike Europa, where tidal heating keeps the ice shell relatively thin and active, Callisto's thick crust has remained stable for billions of years. This stability has allowed the preservation of impact features that would have been erased on more geologically active worlds. It's as if Callisto's surface serves as a museum of the early solar system, preserving evidence of conditions that have been erased elsewhere. The composition of Callisto's surface provides further clues to its history and character. While predominantly water ice, the surface also contains significant amounts of rocky material and dark, carbon-rich compounds. This darker material gives Callisto its distinctly darker appearance compared to Europa and Ganymede, with an albedo of reflecting only about 20% of the sunlight that hits it. The dark material is not uniformly distributed but tends to concentrate in the low-lying areas between the crater rims and ridges. This suggests a process of thermal segregation, where sunlight warms the dark material, causing nearby ice to sublimate and redeposit on higher, cooler areas. Over billions of years, this process has enhanced the contrast between the dark, ice-poor lowlands and the brighter, ice-rich highlands. Close examination of Callisto's smaller-scale surface features reveals an unusual characteristic. Many of the smaller craters appear to have been eroded or degraded, with their rims collapsed and their once sharp features softened. This degradation exceeds what would be expected from micrometeorite impacts alone and suggests that Callisto's icy crust has slowly deformed over time. This slow deformation, or viscous relaxation, is consistent with ice that, while rigid on short timescales, can flow very gradually over millions of years. Callisto possesses an extremely tenuous atmosphere, primarily composed of carbon dioxide with traces of molecular oxygen. This is not a true atmosphere, as we might think of it rather. It's an exosphere, so thin that molecules rarely collide with each other. The oxygen, as on Ganymede, likely results from the breakdown of water ice by charged particles trapped in Jupiter's magnetic field, while the carbon dioxide may be released from carbon-rich compounds in the surface material. Internally, Callisto appears to have remained relatively undifferentiated compared to its siblings, while Io, Europa, and Ganymede have clearly separated into distinct layers of different densities, with heavier materials like metals and silicates forming a core and lighter materials like ice rising to the surface. Callisto's interior seems to be only partially differentiated. Models suggest that while it does have some internal structure, with ice concentrated near the surface and rockier material more abundant at depth, the transition is more gradual than the distinct layers seen in the other moons. This incomplete differentiation provides important clues about Callisto's early history. It suggests that Callisto formed more gradually and experienced less intense heating during its formation than its siblings. The energy of accretion, the process of smaller bodies coming together to form the moon, was likely spread out over a longer period, allowing much of the heat to radiate away rather than accumulating to melt the moon's interior. As a result, the denser materials never fully separated from the lighter ones. The degree of internal differentiation is directly related to the question of Callisto's subsurface ocean. For a moon that appears so undifferentiated and geologically inactive, the evidence for an ocean comes as something of a surprise. The presence of an ocean implies that at least some differentiation must have occurred, with ice separating from liquid water. This seeming contradiction has led scientists to develop models where the differentiation is partial and regional, rather than global and complete. The evidence for an ocean comes primarily from Callisto's interaction with Jupiter's magnetic field. As Callisto orbits Jupiter, it passes through different regions of the planet's massive magnetosphere. If a conductive layer exists within the moon, it should respond to these changing magnetic conditions by generating its own induced magnetic field. The Galileo spacecraft detected precisely such variations in the magnetic field around Callisto, consistent with an electrically conductive layer at depth. While a layer of liquid water mixed with salts provides the most straightforward explanation for this conductivity, some scientists have suggested alternatives. Could the conductivity come from the ice itself, if it contains impurities, or exists in exotic phases, or might it result from some other conductive material within Callisto? The scientific consensus has increasingly favored the subsurface ocean hypothesis, though questions remain about its exact nature and extent. If Callisto does indeed harbor an ocean, what might we expect of it? Unlike the oceans of Europa and Enceladus, which are heated from below by tidal forces and likely interact directly with the rocky core, Callisto's ocean would be sandwiched between layers of ice, much like the situation proposed for Ganymede. The upper boundary would be the base of the thick ice shell, while the lower boundary might be a layer of high-pressure ice forms created by the immense weight of the ocean and ice shell above. The temperature would likely be close to the freezing point throughout much of the ocean, with slightly warmer conditions at greater depths. The pressure would increase with depth, reaching levels that would maintain water in its liquid state, even at temperatures below 0 Celsius. The salt content remains unknown, but would need to be substantial to explain the electrical conductivity inferred from the magnetic field measurements. The age of Callisto's ocean is another intriguing question. If it formed early in the moon's history, it has potentially existed for billions of years, providing a stable environment over geological timescales. Alternatively, if it has waxed and waned over time, it might be relatively young in its current form. The apparent stability of Callisto's ice shell suggests minimal recent interaction between the surface and the ocean, unlike on Europa, where the young, fractured surface implies ongoing exchange between the interior and exterior. Could Callisto's ocean harbor life? The question is perhaps even more challenging than for Europa or Enceladus. The ocean's isolation from both the surface and the rocky interior would limit the exchange of materials and energy that might support living systems. The lower energy environment, with minimal tidal heating, would provide fewer energy sources for potential organisms. However, the very stability of the environment over billions of years could be seen as an advantage, providing ample time for life to emerge and adapt if the basic ingredients were present. Any life in Callisto's ocean would need to thrive in conditions of extreme pressure, near freezing temperatures, and limited energy sources. It would likely be microbial in nature, perhaps analogous to the simplest forms of life found in Earth's deep subsurface or in subglacial lakes in Antarctica. These environments, while extreme by human standards, host microbial communities that have adapted to survive with minimal energy and nutrient inputs. The search for life on Callisto would face significant technical challenges. The thick ice shell, estimated at 150 to 200 kilometers, would be extremely difficult to penetrate with current technology. Unlike Europa and Enceladus, which might provide samples of their oceans through plumes or relatively thin ice regions, Callisto keeps its ocean well isolated. Any mission seeking direct access would need to melt or drill through an enormous thickness of ice, requiring substantial energy sources and highly reliable systems capable of operating for extended periods without human intervention. More realistically, future missions might focus on better characterizing the ocean indirectly, through more detailed measurements of Callisto's magnetic field, gravity field, and subtle changes in its rotation and orbit that could reveal details about its internal structure. Ground-penetrating radar could potentially map the upper portion of the ice shell and possibly detect the ice-ocean boundary if the ice is sufficiently transparent to radio waves. The European Space Agency's JUICE Mission Jupiter Icy Moons Explorer, scheduled to launch in 2023, will conduct multiple flybys of Callisto during its time in the Jovian system. While it will focus primarily on Ganymede, its observations of Callisto will provide valuable new data about this enigmatic world. NASA's Europa Clipper, while focused on Europa, may also contribute to our understanding of the Jovian system as a whole, including Callisto. Callisto's combination of an ancient, preserved surface and a potentially habitable subsurface ocean creates a fascinating juxtaposition. Above lies a landscape virtually unchanged since the earliest days of our solar system, a record of the violent processes that shaped the worlds we know today. Below may lie a hidden sea, dark and cold yet possibly nurturing forms of life that have evolved in isolation for eons. This duality makes Callisto a valuable target for exploration, offering insights into both the past and the possibilities of the present. As we contemplate the nature of Callisto's hidden ocean, we're drawn to the contrasts it presents. It may be the most isolated substantial body of liquid water in our solar system, protected from space by a thick ice shell and separated from the rocky interior by high-pressure ice forms. Yet this very isolation may have preserved conditions that have changed elsewhere, creating a sort of time capsule of the early solar system's aqueous environment. In the grand narrative of Jupiter's moons, Callisto plays a unique role. While Io tells the story of extreme tidal heating and volcanic activity, Europa of ice tectonics and ocean surface interactions, and Ganymede of magnetic field generation and internal complexity, Callisto speaks of preservation and patience. Its value lies not in dynamic processes we can observe in real time, but in the record it maintains of processes long past and the potential it holds for discoveries yet to come. In the cold reaches of Saturn's orbit, nearly 10 times farther from the Sun than Earth, floats a world unlike any other in our solar system. Titan, Saturn's largest moon, stands apart from all other planetary satellites, wrapped in a thick, hazy atmosphere that obscures its surface from ordinary view. For centuries, this cloud-covered world remained a mystery, a tantalizing orange disk, visible through telescopes but revealing none of its secrets. When the Voyager spacecraft flew past in the early 1980s, they confirmed the presence of Titan's substantial atmosphere but could not penetrate the haze. It wasn't until 2004, when the Cassini spacecraft arrived carrying the Huygens probe, that humanity finally glimpsed what lies beneath those clouds. What we discovered was astonishing: a world with a hydrological cycle reminiscent of Earth's, but operating at temperatures so cold that water exists only as rock-hard ice. Instead of water, it is methane and ethane that fall as rain, flow as rivers, collect in lakes, and evaporate back into the atmosphere. Titan, we learned, is the only world besides Earth known to have standing bodies of liquid on its surface. But this surface liquid is only one part of Titan's water story. Deep beneath the frozen crust of this frigid moon, planetary scientists now believe, lies another ocean not of methane or ethane, but of liquid water mixed with ammonia. as alien to the surface hydrocarbons as Earth's oceans would be. Titan is a giant among moons, larger even than the planet Mercury, with a diameter of 5,150 kilometers. Its substantial size gives it enough gravity to hold onto its thick atmosphere, which is primarily nitrogen with a significant component of methane. The atmospheric pressure at Titan's surface is about 1.5 times that on Earth, the only moon in the solar system with a denser atmosphere than our home planet. This thick blanket of air creates a substantial greenhouse effect. Though given Titan's great distance from the Sun, the surface still averages a frigid, negative 180 degrees Celsius. At these temperatures, water ice behaves like rock on Earth, hard, brittle, and forming the foundation of the landscape. Methane takes on the role that water plays on Earth, existing as gas in the atmosphere, liquid on the surface, and solid ice in some locations. This methane cycle, however, presents a scientific puzzle. Sunlight breaks down methane molecules in Titan's upper atmosphere relatively quickly in geological terms, meaning that without some replenishment mechanism, all of Titan's atmospheric methane should have disappeared millions of years ago. The continued presence of methane suggests active processes are releasing it from reservoirs within Titan, perhaps from its subsurface water ocean, or from methane stored in ice structures called clathrates. The Cassini mission revealed Titan's surface in detail through its radar and infrared instruments, which could penetrate the hazy atmosphere. What emerged was a diverse landscape of mountains, plains, dunes, river channels, and lakes. The most striking features were the dark patches near the poles, particularly concentrated in the North Polar region. These proved to be lakes and seas of liquid methane and ethane, with the largest, called Kraken Mare, spanning some 400,000 square kilometers, roughly the size of the Caspian Sea, on Earth. These hydrocarbon lakes show familiar shoreline features, bays, islands, and what appear to be flooded river valleys. Some have smooth shorelines suggesting gentle slopes, while others have steep margins that might indicate they occupy impact craters or sinkholes. The liquids themselves are not pure methane but mixtures of methane, ethane, and dissolved nitrogen, with compositions that likely vary between different lakes and with the seasons. The existence of these surface liquids is made possible by Titan's cold temperature and atmospheric pressure, which put methane and ethane near their triple points, the conditions where a substance can exist as solid, liquid, or gas. On Earth, water is the only common substance near its triple point under natural conditions. On Titan, methane and ethane play this role, creating a familiar but alien hydrological cycle. Radar images from Cassini revealed an extensive network of channels and valleys across Titan's surface, particularly around the equatorial regions. These appear to be drainage networks created by methane rainfall, though unlike on Earth, the precipitation on Titan is rare but potentially intense. Climate models suggest that decades or even centuries might pass between major rainfall events in a given location, but when the rain comes, it can create flash floods that carve and modify the landscape. The equatorial regions of Titan present another striking feature: vast fields of linear dunes stretching for hundreds of kilometers. These dunes, composed of hydrocarbon particles that form in the atmosphere and fall to the surface, are shaped by Titan's winds and can reach heights of 100 meters or more. Their pattern and direction provide evidence of Titan's wind circulation patterns, which, like Earth's, are influenced by the rotation of the Moon and seasonal changes as it orbits Saturn. But perhaps the most intriguing aspect of Titan is what we cannot directly see: the subsurface water ocean that likely exists deep beneath the frozen crust. Evidence for this hidden ocean comes primarily from measurements of Titan's shape and rotation. Cassini precisely tracked the Moon's gravitational field and observed subtle changes in its rotation over time, revealing that Titan's outer ice shell is not rigidly connected to its interior. Instead, the shell appears to float on a liquid layer, allowing it to rotate slightly differently than the core beneath. Further evidence comes from electrical measurements. Titan's interaction with Saturn's magnetosphere suggests the presence of an electrically conductive layer beneath the surface, consistent with a salty water ocean. Models indicate this ocean likely exists about 50 to 100 kilometers beneath the surface, sandwiched between layers of ice above and a rocky core below. What makes Titan's subsurface ocean particularly interesting is its likely composition. Unlike the relatively pure water oceans of Europa and Enceladus, Titan's ocean probably contains significant amounts of ammonia, which acts as an antifreeze and allows the water to remain liquid at temperatures well below 0 degrees Celsius. This ammonia-water mixture creates a different chemical environment than other ocean worlds in our solar system, with its own unique properties and potential for unusual chemistry. The depth of this ocean remains uncertain, but is estimated to be anywhere from 50 to 300 kilometers, potentially containing more water than all of Earth's oceans combined. The ocean is kept liquid primarily by radioactive decay in Titan's rocky core, with tidal heating playing a lesser role than in moons like Europa. The thick ice shell above provides excellent insulation, trapping this heat and maintaining liquid conditions despite the extreme cold of Titan's surface environment. This creates an extraordinary situation, a world with two completely different types of liquid layers, separated by kilometers of ice. At the surface, lakes and seas of hydrocarbons sit under a nitrogen-methane atmosphere. Deep below, a global ocean of water-ammonia mixture surrounds a rocky core, completely isolated from both the surface environment and the distant sun. The relationship between these two liquid systems, the surface hydrocarbon lakes and the subsurface water ocean, remains one of the most fascinating questions in planetary science. Are they completely separate systems, or might there be some exchange between them through cryovolcanic processes? Might methane from the deep interior make its way to the surface, replenishing the atmospheric methane that is constantly being destroyed by solar radiation? Some features on Titan's surface suggest possible cryovolcanism, the eruption of water ammonia, magma, that freezes upon reaching the frigid surface. The most promising candidate is a feature called Sotra Patera, which shows a 500-meter-high mountain adjacent to a 1,000-meter deep pit, similar in some ways to volcanic features on Earth. If confirmed as cryovolcanic, such features would provide a mechanism for materials from the subsurface ocean to reach the surface, potentially including organic compounds of astrobiological interest. The organic chemistry occurring on Titan makes it a natural laboratory for studying prebiotic processes. In the upper atmosphere, solar ultraviolet radiation and charged particles from Saturn's magnetosphere break apart methane and nitrogen molecules, which recombine to form a complex mix of organic compounds. These include various hydrocarbons and nitriles, some of which are precursors to the amino acids and nucleotides that form the building blocks of life on Earth. These compounds form a haze of tiny particles that slowly settle out of the atmosphere onto Titan's surface, where they accumulate over time. Some scientists have calculated that over the age of the solar system, a layer of organic material hundreds of meters thick could have formed across Titan's surface. This creates a scenario where complex organic chemistry is occurring both in the atmosphere and on the surface, while liquid water exists in the subsurface, separated from these organics by a thick ice barrier. Could the water ocean and the surface organics ever mix? This is a crucial question for Titan's potential habitability. On Earth, the chemistry of life is based on reactions that occur in liquid water, using carbon-based organic compounds as building blocks. On Titan, the ingredients are all present but separated organics on the surface, liquid water below. Some models suggest that impacts from asteroids or comets could create temporary melt pools on the surface, allowing surface organics to mix with liquid water for periods lasting hundreds to thousands of years before refreezing potential windows for complex chemical evolution. Alternatively, the ice shell itself might not be a perfect barrier. Fractures or areas of convection within the ice might allow some exchange of materials between the surface and subsurface. Or cryovolcanic processes might bring water-ammonia mixtures to the surface, where they could interact with the accumulated organics before freezing. These processes might be rare or localized, but over Titan's 4.5 billion-year history, many opportunities for such interactions may have occurred. The chemistry possible in Titan's water-ammonia ocean would differ from that in pure water. Ammonia creates strongly alkaline conditions, which favor certain types of chemical reactions over others. It can also act as a solvent for organic compounds that might not dissolve readily in pure water. These properties could enable unique chemical pathways not found in other ocean worlds of the outer solar system. Additionally, the interface between the ocean and the overlying ice shell could provide interesting chemical and thermal gradients. On Earth, the boundaries between different phases or environments often support higher biological diversity and activity. The boundary between Titan's ice shell and its subsurface ocean could create similar gradient environments where energy and materials flow between different states. The rocky core beneath the ocean would also play a crucial role in the ocean's chemistry and potential habitability. Water-rock interactions would release minerals and heat into the ocean, potentially providing chemical energy sources similar to those that power ecosystems around hydrothermal vents on Earth's seafloor. The exact composition of Titan's core remains uncertain, but it likely contains silicate minerals and metals that could participate in geochemical cycles with the ocean above. Titan's distance from the Sun and its thick atmosphere shield its surface and subsurface from much of the harmful radiation that bombards other bodies in the solar system. This relative protection could be advantageous for any hypothetical life, reducing one of the stresses that organisms would face. The stable conditions in the subsurface ocean, which has likely existed for much of solar system history, would provide a consistent environment for chemical or biological evolution over long time periods. However, the extreme cold of Titan also presents challenges for life as we know it. Chemical reactions generally proceed more slowly at lower temperatures, which could impede the development of complex chemistry. The subsurface ocean, while warmer than the surface, would still be cold by Earth standards, perhaps as cold as -20 to -40 degrees Celsius, maintained in a liquid state only by the antifreeze effect of the ammonia. Life in such cold environments would need specialized adaptations to function. Despite these challenges, Titan provides a unique, natural laboratory for studying organic chemistry under conditions radically different from Earth. Its atmosphere, surface, and subsurface represent three distinct chemical environments, each with its own set of reactions and processes. Understanding the interplay between these environments could provide crucial insights into the potential diversity of chemical and potentially biological systems beyond Earth. The methane cycle on Titan presents its own set of scientific puzzles. On Earth, the carbon cycle includes biological components, with plants removing carbon dioxide from the atmosphere and animals returning it through respiration. On Titan, the methane cycle lacks a known biological component, yet the continued presence of atmospheric methane, despite processes that destroy it, suggests some active replenishment mechanism. Could there be processes on Titan that mimic biology in some ways, cycling methane between different forms? Or is the replenishment primarily geological, with methane escaping from the interior through cracks or cryovolcanic features? Some scientists have even speculated about the possibility of methanogenic life in Titan's subsurface ocean, producing methane as a metabolic byproduct that eventually makes its way to the atmosphere, though such scenarios remain highly speculative. The seasonal changes on Titan add another layer of complexity to this already fascinating world. Titan's year lasts 29.5 Earth years, following Saturn's orbit around the Sun. This creates extremely long seasons, with each lasting about 7 Earth years. Cassini observed Titan for 13 years, capturing parts of 2 Titan seasons, and witnessed significant changes in cloud patterns and surface features. One of the most dramatic seasonal changes occurs in the distribution of clouds and rainfall. During Titan's northern winter, clouds were predominantly observed in the southern hemisphere. As the seasons shifted toward northern spring, clouds began forming around the equator and then in the northern hemisphere. This pattern suggests that rainfall and surface liquid distributions may shift between hemispheres over the course of a Titan year. Indeed, observations of the southern polar region showed changes in some of the lakes there, with some appearing to shrink or disappear entirely as the season progressed from summer to fall. This suggests active evaporation of liquid methane under the slightly warmer conditions of summer, followed by condensation and rainfall in the opposite hemisphere. The northern polar region, with its larger and apparently more permanent lakes, may serve as the main reservoir in this global methane cycle. The liquid bodies themselves show fascinating dynamics. Radar observations revealed changes in the shorelines of some lakes, suggesting rising or falling liquid levels. In one southern hemisphere lake, named Ontario Lacus, the shoreline receded several kilometers over the period of Cassini's observations, consistent with evaporation during the southern summer. In the northern hemisphere, observations suggested that some smaller lakes might have formed or expanded following the transition from winter to spring. Perhaps most intriguing was the observation of what appeared to be a specular reflection mirror, like glint from the northern region, before Cassini's cameras could directly image the lakes there. This reflection, like sunlight bouncing off a mirror, provided early evidence for liquid surfaces in the northern hemisphere. Later radar observations confirmed extensive lakes and seas in this region, including not only the massive Kraken Mare, but also Ligeia Mare and Punga Mare, each covering tens of thousands of square kilometers. The composition of these liquid bodies likely varies both between different lakes and with depth within a single lake. Methane evaporates more readily than ethane, potentially leading to stratification within deeper lakes, with more methane-rich layers near the surface and ethane-rich layers at depth. This stratification might create distinct chemical environments at different depths, similar to the way temperature and salinity create layers in Earth's oceans. The shorelines of Titan's lakes show diverse features that suggest complex interactions between the liquids and the surrounding landscape. Some appear to have flooded valleys, suggesting they lie in topographic depressions that filled with liquid. Others have steep margins that might indicate they occupy impact craters or sinkholes formed by dissolution of surface materials. Still others appear to have changed in extent over the period of observation, suggesting active hydrological processes. One particularly interesting feature is the apparent absence of large waves on Titan's lakes. Cassini's radar observations showed surfaces that appeared remarkably smooth, with any waves present being less than a few millimeters in height. This tranquility might result from either very low wind speeds at the time of observation, or from the physical properties of liquid methane and ethane, which have lower surface tension than water and might dampen wave formation. The river channels observed on Titan's surface tell a story of rare but significant rainfall events. Many appear dry most of the time, but show clear evidence of having carried liquid in the past. Some form complex dendritic networks similar to river systems on Earth, while others appear as relatively straight channels that might follow fractures in the ice crust. The distribution of these channels across Titan's surface suggests that rain falls globally, not just near the poles where the lakes are currently concentrated. Among the most spectacular features is a channel system named Xanadu, which extends for over 400 kilometers across Titan's surface. The network of branching tributaries, main channels, and what appear to be alluvial deposits at its mouth bear striking similarities to large river systems on Earth. The scale and complexity of this system suggest repeated or sustained flow over geological time, rather than rare, brief events. The dune fields that dominate Titan's equatorial regions provide another window into the Moon's complex processes. These linear dunes, visible in radar images as dark streaks against a brighter background, extend for hundreds of kilometers, aligned generally east to west. They're composed not of sand as on Earth, but of solid hydrocarbon particles that likely formed in the atmosphere and settled to the surface. Their alignment provides evidence of Titan's prevailing wind patterns, which appear to be influenced by its rotation in ways similar to Earth's trade winds. Between the dune fields and the polar lakes lie regions of varied terrain, including what appear to be plains, highlands, and isolated mountain ranges. The highest peaks observed rise about 1,000 meters above the surrounding terrain, modest by Earth standards but significant in Titan's lower gravity environment. The exact composition and origin of these mountains remain uncertain, but they may represent blocks of water ice crust that have been uplifted or tilted by tectonic processes, driven by cooling and contraction of Titan's interior. The surface composition overall is a mix of water ice, which forms the structural bedrock of Titan, and organic compounds that have settled from the atmosphere. These organics include a diverse array of hydrocarbons and nitriles, which may undergo further reactions on the surface to form increasingly complex molecules. The constant influx of these compounds from the atmosphere, combined with the occasional rainfall of liquid methane, creates a dynamic surface chemistry unlike anything else in our solar system. Beneath this organic-rich surface lies the water ice crust, estimated to be tens to 100 kilometers thick. This crust is not likely pure water ice, but a mix of water ice with other compounds, potentially including methane, clathroteskage-like ice structures that trap methane molecules within them. These clathrates could serve as a reservoir for methane, releasing it gradually to replenish the atmosphere. The subsurface water ammonia ocean begins beneath this crust, extending potentially hundreds of kilometers down before reaching the rocky core. The boundary between the ice crust and the ocean may not be sharp, but could involve a layer of slushy, partially frozen material. Similarly, the boundary between the ocean and the core might include a layer of high-pressure ice forms created by the immense weight of the ocean above, similar to what is postulated for Ganymede. The internal structure, as a whole, shows evidence of being only partially differentiated, not fully separated into distinct layers of different densities, as in some other moons. This suggests a relatively slow formation process that allowed heat to dissipate rather than building up to completely melt the interior. The result is an interior with some structure, but without the sharp boundaries that characterize fully differentiated bodies like Io or Europa. Titan's complex environment, with its atmospheric chemistry, surface hydrocarbon lakes, and subsurface water ocean, makes it one of the most intriguing targets for astrobiological research. It offers multiple potential habitats for life as we know it, or, perhaps more intriguingly, for life as we don't know it life, with a different chemical basis than Earth's water and carbon-based biochemistry. The conventional view of habitability focuses on liquid water, which exists on Titan only in the subsurface ocean. This environment, while cold and ammonia-rich, contains the basic ingredients needed for life, as we understand it: liquid water, organic compounds, and energy sources from water-rock interactions. If this environment has remained stable over geological timescales, it could have provided ample opportunity for chemical evolution. But Titan also opens the door to more speculative possibilities. Could the hydrocarbon lakes on the surface support some exotic form of life using liquid methane or ethane as a solvent instead of water? Such life would need biochemistry radically different from Earth's, operating at extremely low temperatures and using different types of chemical bonds and reactions. While such scenarios remain purely hypothetical, Titan is one of the few places in our solar system where the necessary conditions stable bodies of liquid and complex organic chemistry exist for such possibilities to be considered. Looking to the future, Titan presents tantalizing opportunities for exploration. NASA's Dragonfly mission, scheduled to launch in 2027 and arrive at Titan in 2034, will send a rotorcraft lander to explore the moon's surface and atmosphere. Equipped with instruments capable of detecting complex organic molecules and measuring atmospheric and surface properties, Dragonfly will provide unprecedented insights into Titan's chemistry and potential habitability. The mission will focus primarily on the surface and lower atmosphere, sampling different regions to understand the distribution and complexity of organic compounds. It will not directly investigate the subsurface ocean, though its measurements may provide indirect evidence of interactions between the deep interior and the surface. Future missions might target the subsurface more directly, perhaps using seismic instruments to characterize the ice shell and ocean beneath. As we contemplate Titan's complex environment, we're struck by the remarkable parallels and contrasts with Earth. Both worlds have nitrogen-dominated atmospheres, active hydrological cycles, and diverse surface features shaped by liquids and winds. Yet they operate at vastly different temperatures and with different chemical systems: water on Earth, hydrocarbons on Titan's surface, and a hidden water, ammonia, ocean beneath. Titan reminds us that familiar processes can occur with unfamiliar materials, and that the boundary between the exotic and the ordinary is often a matter of temperature, pressure, and chemical context. In studying this distant moon, we gain not only knowledge of another world but a deeper perspective on our own, seeing Earth's processes in a broader context that expands our understanding of what is possible in planetary environments. As the Cassini mission's legacy continues to inform our understanding of Titan, and as we anticipate the new discoveries awaiting Dragonfly, we're reminded that exploration often reveals worlds more complex and fascinating than we could have imagined. In Titan's oranges haze, hydrocarbon lakes, and hidden water ocean, we find a moon of magnificent contrasts and extraordinary possibilities, a world that challenges our definitions and expands our horizons as we seek to understand the diversity of environments our solar system has created. Far beyond the orbit of Neptune, where sunlight dims to a mere twilight glow, drifts a class of worlds long considered the frozen outposts of our solar system. Here, where temperatures plunge below -220 degrees Celsius, conventional wisdom once suggested that any water would be frozen, solid, locked in eternal ice. Yet as our robotic explorers push deeper into the solar system, we're discovering that even in these remote regions, liquid water might persist beneath icy crusts. expanding our understanding of where habitable environments might exist. The story of distant ocean worlds begins with a dramatic shift in our understanding of Pluto. For decades after its discovery in 1930, Pluto was considered the ninth planet of our solar system, a tiny, frigid world so distant that even the most powerful telescopes revealed little more than a fuzzy dot. As telescopes improved, astronomers discovered that Pluto was smaller than originally thought, smaller even than Earth's moon, and that it possessed at least one sizable satellite of its own, Charon. But the true revelation awaited NASA's New Horizons spacecraft, which after a journey of 9.5 years, flew past the Pluto system in July 2015. The images and data New Horizons sent back transformed our understanding of this distant world. Rather than a static, heavily cratered ball of ice like many expected, Pluto revealed itself to be geologically active, with diverse terrains including mountains of water ice that rival the Rocky Mountains in height, vast plains of nitrogen ice showing signs of glacial flow, and regions with surprisingly few impact craters, suggesting surfaces young enough that the constant bombardment of space hasn't had time to leave its mark. Most intriguing was a vast, heart-shaped feature on Pluto's surface, informally named Tumbor Regio, after Pluto's discoverer, Clyde Tombaugh. The left lobe of this heart, called Sputnik Planitia, is a depression filled with nitrogen ice that shows evidence of convection. The ice appears to be flowing in large cells, like a gently simmering pot of thick stew, but operating over geological timescales. This activity requires heat from Pluto's interior, challenging the assumption that small, distant worlds would be geologically dead. The evidence for a subsurface ocean came from several lines of investigation. First, the location of Sputnik Planitia, which lies directly opposite from Charon, suggests it represents a massive positive gravity anomaly, an extra concentration of mass. This position is what would be expected if Pluto's interior deformed to reach a minimum energy state in its rotation with Charon. But Sputnik Planitia is actually a depression filled with nitrogen ice, which should represent a negative gravity anomaly. The best explanation is that beneath this region lies a subsurface ocean, a layer of dense, salty liquid water that provides the extra mass needed to explain the feature's position. Further evidence came from the network of tectonic features observed across Pluto's surface. Long fractures and fault lines suggest the dwarf planet has experienced global expansion at some point in its history, which could be explained by the freezing of a subsurface ocean. When water freezes, it expands, potentially cracking the crust above. The pattern of these fractures is consistent with models of how an internal ocean would freeze and expand over time. If Pluto does indeed harbor a hidden ocean, how has it remained liquid for billions of years so far from the Sun? The answer likely lies in a combination of factors. Radioactive decay of elements in Pluto's rocky core would provide a steady, long-lived heat source. The ice shell above would act as an insulating blanket, trapping this heat inside. And crucially, the ocean may contain significant amounts of ammonia or other compounds that act as antifreeze, lowering the freezing point of water substantially. The thickness of Pluto's ice shell and the depth of the potential ocean remain uncertain. Models suggest the ice might be anywhere from 150 to 200 kilometers thick, with the ocean perhaps another 100 to 200 kilometers deep. This would mean the ocean constitutes a significant fraction of Pluto's total volume, despite being hidden from direct observation. The composition of this ocean is a subject of speculation, though clues come from surface materials that might originate from below. The presence of ammonia compounds on Pluto's surface suggests the ocean might be rich in ammonia, which would lower its freezing point to around -100 degrees Celsius. Salts are also likely present, further depressing the freezing point and increasing the density of the liquid. What's particularly stunning about the possibility of an ocean within Pluto is how it challenges our assumptions about habitability in the solar system. Traditional definitions of the habitable zone focus on the range of distances from a star where a planet's surface temperature allows for liquid water. By this definition, Pluto lies far outside the Sun's habitable zone. Yet if liquid water exists beneath its surface, maintained by internal heat and chemical antifreeze, we must expand our understanding of where habitable environments might be found. And Pluto may not be alone. As we've explored the outer solar system more thoroughly, we've discovered a family of worlds beyond Neptune collectively known as trans-Neptunian objects, or TNOs. The largest of these, like Pluto, have been classified as dwarf planets. Could they too harbor subsurface oceans? Eris, slightly more massive than Pluto though, similar in size, orbits nearly twice as far from the Sun. Its high density suggests a substantial rocky component that could provide internal heating through radioactive decay. While no spacecraft has yet visited Eris, models based on its size, mass, and probable composition suggest it could potentially maintain a subsurface ocean, though perhaps more deeply buried and more thoroughly frozen than Pluto's. Makemake, another dwarf planet in the Kuiper Belt, has a bright surface suggesting a coating of methane ice. Less dense than Pluto or Eris, it may contain a lower proportion of rock and thus have less internal heating from radioactive decay. This might make a substantial liquid layer less likely, though not impossible, if sufficient antifreeze compounds are present. Haumea presents a particularly unusual case. This dwarf planet has an elongated shape, spinning rapidly on its axis, with a day lasting only 4 hours. This rapid rotation has deformed Haumea into an ellipsoid rather than a sphere. Such a shape seems inconsistent with a liquid layer inside, which would allow the world to settle into a more spherical form. However, Haumea's high density and the presence of water ice on its surface suggest a complex history that might have included a liquid phase early in its evolution, even if it is fully frozen today. Beyond the largest TNOs, dozens of smaller bodies orbit in the outer solar system, many with diameters of several hundred kilometers. While individually these might seem too small to maintain liquid water, recent discoveries have suggested that even modest-sized bodies might have the potential for at least temporary liquid water environments. The dwarf planet Ceres, the largest object in the asteroid belt between Mars and Jupiter, has provided intriguing evidence for this possibility. NASA's Dawn mission, which orbited Ceres from 2015 to 2018, found bright spots of salt deposits and evidence of a subsurface layer of briny water, ice, or mud. While not a true ocean, this suggests that even relatively small worlds can maintain some liquid water beneath their surfaces, particularly if salts or other antifreeze compounds are present to lower the freezing point. Even comets, traditionally seen as simply dirty snowballs, have revealed surprisingly complex structures. The European Space Agency's Rosetta mission to Comet 67P, Churyumov-Gerasimenko, found evidence that the comet's interior contains distinct layers and compositional variations, suggesting that as these bodies are warmed by the sun, they can develop complex internal structures that might include temporarily liquid regions. What these discoveries collectively suggest is that subsurface oceans might be far more common in our solar system than previously thought. Rather than being limited to a few exceptional moons like Europa and Enceladus, liquid water environments might exist within numerous worlds, including many that seem, from the outside, to be merely frozen balls of ice and rock. This realization has profound implications for our understanding of habitability. If liquid water environments can exist so far from the sun, maintained by internal heat and chemical antifreeze, then similar environments might be common around other stars as well. Moons orbiting giant planets in other solar systems, or dwarf planets in the outer reaches of those systems, might harbor hidden oceans regardless of their distance from their parent star. The habitability of these distant ocean worlds would depend on several factors beyond simply the presence of liquid water. The chemical composition of the ocean is crucial. On Earth, life utilizes not just water, but a complex suite of dissolved minerals and organic compounds. A habitable subsurface ocean would need a similar chemical diversity, which would likely depend on interactions between the liquid water and a rocky core. This might represent a challenge for worlds like Pluto, where the ocean may be sandwiched between layers of ice rather than in direct contact with a rocky interior. However, over geological timescales, even small amounts of material exchange between the ocean and core could establish the necessary chemical inventory. Additionally, impacts from comets and asteroids throughout the solar system's history would have delivered organic compounds to these worlds, potentially providing some of the chemical building blocks for life. Energy sources would represent another requirement. Deep in these hidden oceans, far from the sun's light, any life would need to rely on chemical energy rather than photosynthesis. On Earth, Ecosystems around deep-sea hydrothermal vents thrive on chemical energy from the reaction between certain minerals and seawater. Similar energy sources might exist within these distant ocean worlds, particularly if water from the ocean can interact with the rocky core. The timescale over which these oceans have existed is another important consideration. If they formed early in the solar system's history and have remained stable for billions of years, they would have provided ample time for complex chemistry to develop and potentially for life to emerge. If, on the other hand, they are transient features, freezing and thawing over shorter timescales, they might be less conducive to the emergence of life. The temperatures within these oceans, while cold by Earth standards, might not be prohibitively so for life. On Earth, microorganisms have been found living in supercooled brines with temperatures as low as -20 degrees Celsius. If the oceans of distant worlds contain sufficient antifreeze compounds to remain liquid at such temperatures, they might not be too cold for certain forms of life to survive. Pressure could present another challenge. At the depths where these oceans likely exist, under kilometers of ice, pressures would be extreme. However, high-pressure environments also exist on Earth, in the deepest ocean trenches, where organisms have adapted to survive. The pressures in distant subsurface oceans might be even higher, but not necessarily beyond the theoretical limits for biological structures. Exploring these distant ocean worlds presents enormous technical challenges. Their great distance from Earth makes missions lengthy and communication delayed. The substantial ice shells that likely cover their oceans would be difficult to penetrate with current technology, and the extreme cold would complicate operations for any spacecraft designed to land on their surfaces. Nevertheless, future missions may provide more evidence for these hidden oceans. NASA has proposed a mission called Trident that would fly by Neptune's moon Triton, which shows evidence of recent geological activity and might harbor a subsurface ocean of its own. The European Space Agency is developing plans for the Comet Interceptor mission, which would study a pristine comet and could provide insights into the internal structure of these icy bodies. In the more distant future, missions might deploy sophisticated ice-penetrating radar to map subsurface oceans from orbit, or even attempt to access these oceans directly, perhaps through naturally occurring features like cryovolcanic vents, where material from below reaches the surface. As we contemplate these distant ocean worlds, we're reminded of how profoundly our understanding of our solar system has changed in recent decades. What once seemed a collection of mostly static, frozen worlds beyond the orbit of Mars has revealed itself to be a dynamic system with active geology and potentially habitable environments extending all the way to its outer reaches. The definition of what constitutes a habitable zone has expanded from a narrow ring around the Sun to a much broader concept that includes subsurface environments maintained by internal heat, chemical antifreeze, and insulating ice shells. This expanded definition dramatically increases the potential real estate for life, not just in our solar system, but throughout the universe. Pluto and its kin teach us humility in our assumptions about where life might exist. Even in the cold, dim outskirts of our solar system, warmth and liquid water persist, hidden beneath icy crusts, but there nonetheless. As we continue to explore these distant realms, we must remain open to the possibility that habitability extends much further and takes many more forms than we once imagined. At first glance, it seems impossible. How could liquid water exist on worlds so distant from the Sun that surface temperatures plunge below -180 degrees Celsius? By all rights, these moons and dwarf planets should be solid ice throughout, frozen from surface to core. Yet, as we've discovered, many harbor vast oceans beneath their icy crusts. The answer to this apparent paradox lies not primarily in the distant warmth of the Sun, but in a fundamental force of nature that operates throughout the cosmos gravity, and specifically, the phenomenon known as tidal heating. To understand tidal heating, we must first understand tidal forces themselves. When we think of tides, we typically imagine the rise and fall of Earth's oceans under the gravitational influence of the Moon and, to a lesser extent, the Sun. These celestial bodies pull on Earth's oceans, creating bulges that we experience as high tides. As Earth rotates, different locations pass through these bulges, creating the familiar cycle of high and low tides that coastal dwellers observe daily. But tidal forces affect more than just Earth's oceans. They subtly deform the entire planet, causing the solid ground to rise and fall by several centimeters throughout the day. We don't notice this movement because it's gradual and consistent across the landscape, but sensitive instruments can detect this breathing of the Earth. This deformation happens because gravity weakens with distance, so the side of Earth facing the Moon experiences a stronger gravitational pull than the side facing away. This differential pull stretches Earth slightly along the Earth-Moon axis, creating a more ellipsoidal shape than a perfect sphere. For Earth, these deformations are minimal. Our planet is large and rigid enough that the tidal bulges are relatively small compared to its overall size. But imagine a world much closer to a massive planet, like Jupiter or Saturn. The tidal forces would be dramatically stronger, potentially enough to significantly deform the entire body. Now imagine that this world orbits its planet in an elliptical rather than circular path, meaning its distance from the planet varies throughout its orbit. As it moves closer to the planet, the tidal forces intensify, stretching the world more severely. As it moves farther away, the forces weaken, allowing the world to relax back toward a more spherical shape. This constant stretching and relaxing as the Moon orbits in an elliptical path creates friction within its interior. Materials don't deform without resistance. They have what scientists call viscosity, a resistance to flow. As the Moon's interior materials are forced to shift and flow with the changing tidal forces, this resistance generates heat through friction, much as rubbing your hands together warms them. This is tidal heating, the conversion of orbital energy into thermal energy through tidal deformation. The amount of tidal heating a world experiences depends on several factors. The mass of the parent planet is crucial. More massive planets create stronger gravitational fields and thus stronger tidal forces. The size of the Moon matters too. Smaller moons, with less internal gravitational cohesion, can be more easily deformed. But perhaps most important is the eccentricity of the orbitho-elliptical, rather than circular it is. A perfectly circular orbit would create a constant tidal bulge that moves with the Moon, generating minimal friction. A highly elliptical orbit creates a constantly changing tidal force, maximizing the internal friction and heating. This is where orbital resonances become critical. Throughout the solar system, we find systems of moons where orbital periods are locked in simple numerical ratios with each other. For example, Jupiter's moons Io, Europa, and Ganymede are in what's called a Laplace resonance, with Io orbiting Jupiter 4 times for every 2 orbits of Europa and 1 of Ganymede. These resonances aren't coincidental. They arise naturally as moons interact gravitationally, and once established, they tend to be stable over long time periods. The importance of these resonances for tidal heating is that they prevent orbits from becoming perfectly circular, as they otherwise might over time due to tidal interactions with the parent planet. The gravitational tugs from other moons maintain a certain degree of orbital eccentricity, ensuring that tidal forces continue to vary throughout the orbit, sustaining the tidal heating process. Io, Jupiter's innermost large moon, provides the most dramatic example of tidal heating in our solar system. Caught in a resonance with Europa and Ganymede that forces it to maintain an elliptical orbit and orbiting very close to massive Jupiter, Io experiences such intense tidal heating that it has become the most volcanically active body in the solar system. Its interior is largely molten, and its surface is constantly being reshaped by eruptions of sulfurous magma. Io is literally being turned inside out by tidal forces, with an estimated heat flow per square meter higher than that of Earth, despite being much smaller and having far less radioactive material in its interior. Moving outward from Jupiter, we find Europa, also caught in the Laplace resonance. While it orbits farther from Jupiter than Io, and thus experiences weaker tidal forces directly, it still maintains enough orbital eccentricity to generate significant internal heating. This heating is not enough to melt the entire Moon as with Io, but more than sufficient to maintain a global subsurface ocean beneath its icy crust. Without this tidal heating, Europa would likely be frozen solid given its distance from the Sun. Similarly, Saturn's moon Enceladus is in a resonance with the larger moon Dione, with Enceladus orbiting Saturn exactly twice for every orbit of Dione. This resonance helps maintain Enceladus's slightly elliptical orbit, creating the tidal heating that powers its spectacular south polar geysers and maintains its subsurface ocean, despite its small size and distance from the Sun. Titan, though also orbiting Saturn, has a nearly circular orbit and experiences less tidal heating than Enceladus. Its subsurface water ocean is maintained more by its internal radioactive decay and the insulating properties of its thick ice shell. However, even Titan's modest tidal heating contributes to keeping its interior warm enough for a liquid layer to persist. The mechanics of tidal heating work within these moons, much as they do within Earth, but with greater intensity and different materials. As tidal forces deform the moon, different layers respond differently based on their composition and physical state. Rocky materials are relatively rigid and resist deformation, generating significant friction and heat when forced to flex. Ice is more compliant at temperatures near its melting point, but can behave rigidly when very cold. Liquid layers, like subsurface oceans, transmit tidal forces differently, creating complex patterns of stress and strain within the moon's structure. Computer models suggest that tidal heating is not uniform throughout these moons but concentrates in specific regions, where the physical properties of materials and the geometry of the tidal forces combine to maximize friction. This can create hotspots within the interior, potentially leading to upwelling currents in subsurface oceans or localized melting in otherwise solid layers. The effects of tidal heating extend beyond simply keeping water liquid. The heat drives geological activity, creating the fractures and ridges we observe on Europa's surface, the geysers of Enceladus, and potentially cryovolcanic features on several other moons. This activity enables material exchange between the subsurface ocean and the surface, potentially bringing nutrients and energy sources from the interior to environments where they could support life. Tidal heating also establishes temperature gradients within these worlds. Heat flowing from the interior toward the surface creates variations in temperature with depth, which in turn can drive convection in both the ice shell and the subsurface ocean. These vertical movements transport materials and energy, creating a more dynamic environment than would exist in a uniformly cold body. The interplay between tidal heating and a moon's physical structure creates feedback loops that help regulate the heating process. As a region heats up, its materials may become less viscous and more easily deformed, potentially reducing the friction and thus the heating. Conversely, if an area cools and becomes more rigid, it may experience increased friction and heating when deformed by tidal forces. These feedback mechanisms help explain how tidal heating can reach a relatively stable state rather than continuously increasing or decreasing. The timescale over which tidal heating operates is vast, typically billions of years. This long-term, stable energy source is crucial for the potential habitability of subsurface oceans. While the heat output may fluctuate somewhat over time, particularly if orbital resonances evolve or if the physical properties of the moon change significantly, the basic process remains active as long as the orbital configuration sustains it. This longevity stands in contrast to the heating that would come purely from radioactive decay or from the energy of formation. These sources naturally diminish over time as radioactive elements are depleted or as the initial heat of accretion radiates away. Tidal heating, driven by ongoing orbital dynamics, can provide a renewable energy source that persists throughout a moon's history. The tidal heating process also explains why some moons in the outer solar system have subsurface oceans, while others apparently do not. The orbital configurations and internal structures must align in specific ways to generate and trap sufficient heat. Callisto, Jupiter's outermost large moon, orbits too far from Jupiter to experience strong tidal forces. It also isn't captured in a resonance that would force an elliptical orbit. As a result, it experiences much less tidal heating than its inner neighbors, though it may still harbor a subsurface ocean, maintained primarily by radioactive decay and insulation. Similarly, many moons in the Saturn system show no evidence of substantial tidal heating or subsurface oceans. They either orbit too far from Saturn, have orbits too nearly circular, or lack the internal structure that would efficiently convert tidal deformation into heat. The specific combination of conditions needed for significant tidal heating explains why ocean worlds, while more common than once thought, are still special places in our solar system. For Pluto and other distant dwarf planets, tidal heating plays a more limited role. Pluto and its largest moon, Charon, are tidally locked to each other, both showing the same face to the other at all times. This locking minimizes the ongoing tidal deformation and heating, though it suggests a period of intense tidal heating in the past before the locking was established. The subsurface ocean that may exist within Pluto today is likely maintained primarily by radioactive decay in its rocky core and the insulating properties of its ice shell, with ammonia or other compounds acting as antifreeze. When we examine a world like Europa or Enceladus, we're not just seeing the effects of current tidal heating, but the cumulative impact of this process over billions of years. The fractured surfaces, the layered interiors, the chemical compositions of their ocean soil bear the influence of eons of tidal forces, reshaping these worlds from within. The discovery of so many tidally heated ocean worlds in our solar system raises intriguing possibilities for exoplanetary systems. Moons orbiting gas giants in other star systems might experience similar tidal heating, potentially creating habitable environments, even in systems where the planet itself orbits outside the conventional habitable zone of its star. As our detection methods improve, and we begin to discover and characterize exomoons, tidal heating will be a crucial factor in assessing their potential habitability. Moreover, the same principles apply to binary planet systems and certain types of exoplanets. Close binary systems like Pluto-Charon experience mutual tidal forces. Exoplanets in very close orbits around their stars, like those in the TRAPPIST-1 system, may experience significant tidal heating from their stars. Exoplanets with large moons may both drive and experience tidal heating. The principles that keep Europa's ocean liquid may operate throughout the galaxy, creating potential habitats for life in unexpected places. The physics of tidal heating is universal, governed by the same gravitational laws that operate throughout the cosmos. What we've learned from studying ocean worlds in our solar system provides a framework for understanding how similar worlds might exist around other stars. The specific conditions will vary: different parent bodies, different orbital parameters, different internal compositions, but the fundamental process remains the same: the conversion of orbital energy into heat through tidal deformation. To understand this process in more detail, consider what happens within a moon like Europa as it orbits Jupiter. When Europa is at its closest approach to Jupiter, the giant planet's gravity pulls most strongly on the near side of the moon, creating a pronounced tidal bulge. As Europa moves away to the most distant part of its orbit, this bulge should diminish as Jupiter's gravitational pull weakens. However, solid materials resist rapid deformation, causing the bulge to lag behind the changing gravitational force. This lag creates a torque as Jupiter's gravity pulls on the off-center bulge. The torque affects Europa's rotation and orbital evolution, but more importantly for our purposes, it creates stress within the moon's structure. Different layers, the icy crust, the subsurface ocean, the rocky, correspond differently to these stresses, moving slightly relative to each other. The friction between these layers, and within each layer as different parts move relative to each other, generates heat. The amount of heat generated depends on the physical properties of the materials, particularly their viscosity, which determines how readily they flow when stressed. The rocky core, being relatively rigid, experiences high friction when deformed. The liquid ocean transmits stresses differently, with water molecules sliding past each other easily, but potentially creating friction at boundary layers. The ice shell's behavior varies with depth and temperature, with colder, more brittle ice near the surface, and warmer, more plastic ice at depth. Computer models suggest that for moons like Europa, much of the tidal heating occurs in the rocky core rather than in the ice shell. This creates a bottom heating scenario, with warmth flowing from the core up through the ocean and eventually through the ice to be radiated into space. This heat flow establishes the temperature gradient that keeps the ocean liquid while maintaining a frozen crust at the surface. For smaller moons like Enceladus, the distribution of tidal heating may be different. Its south polar region shows concentrated geological activity, suggesting either focused tidal heating in that area or more efficient transport of heat from the interior to the surface there. The tiger stripe fractures that emit its geysers may provide pathways for heat from deeper layers to reach the surface more directly than elsewhere on the moon. The specific orbital resonances that enable tidal heating in different moons have their own fascinating histories. These resonances didn't necessarily exist when the moons first formed, but evolved over time through gravitational interactions. As moons orbit their parent planet, they raise tidal bulges not just within themselves, but within the planet as well. These bulges create torques that gradually change the moon's orbits. Over millions to billions of years, these subtle forces can lock moons into resonant orbits with each other. Once established, these resonances are often stable over long time periods, creating the sustained orbital eccentricity needed for ongoing tidal heating. The Laplace resonance among Io, Europa, and Ganymede is particularly robust, having persisted for much of the Jovian system's history. The interplay between tidal heating and a moon's interior structure creates another fascinating dynamic. As tidal heating warms the interior, some originally solid materials may melt, changing their physical properties. These changes affect how efficiently tidal forces are converted to heat, potentially creating feedback loops that help regulate the heating process. In the case of Europa, models suggest that if tidal heating became too intense, more of the ice shell would melt, making the remaining shell thinner and more easily deformed. This more compliant shell would generate less friction when deformed by tidal forces, reducing the heating. Conversely, if heating decreased and more of the ocean froze, the thicker ice shell would be more resistant to deformation, potentially generating more friction and heating when subjected to tidal forces. These feedback mechanisms may help explain how subsurface oceans can persist in relatively stable states over geological timescales. The relationship between tidal heating and other heat sources within these moons adds another layer of complexity. Radioactive decay of elements like uranium, thorium, and potassium in rocky materials provides a baseline of heating in all substantial bodies in the solar system. This radiogenic heating was more intense early in the solar system's history, when short-lived radioactive isotopes were still abundant, and has gradually diminished over time. For larger moons like Ganymede, radiogenic heating in the rocky core likely contributes significantly to maintaining the subsurface ocean, working in concert with the tidal heating from Jupiter and insulation from the ice shell. For smaller bodies like Enceladus, the relatively small volume of rocky material means less radiogenic heating, making tidal forces the dominant heat source. The initial heat of formation, the energy released as a body accretes from smaller objects, and as materials within it differentiate into layers of different density also played a role, particularly early in these moons' histories. This primordial heat set the initial conditions for the moon's thermal evolution, potentially creating the first subsurface oceans even before tidal heating became established in its current form. As we examine ocean worlds throughout the solar system, we see variations on the tidal heating theme, each playing out according to the specific characteristics of the world in question. Io, intensely heated, has no subsurface ocean because the tidal forces are strong enough to melt rock, creating a partially molten interior. Europa and Enceladus, with moderate tidal heating, maintain liquid water oceans between icy crusts and rocky cores. Ganymede and Titan, with less intense tidal heating, may have oceans sandwiched between different forms of ice, rather than directly contacting their rocky cores. The history of our understanding of tidal heating reflects the broader evolution of planetary science. When the Voyager spacecraft first revealed Io's volcanic activity in 1979, the scientific community was stunned. The idea that a small moon so far from the Sun could be volcanically active challenged conventional wisdom about heat sources in the outer solar system. Stanton Peele, Patrick Casson, and Raymond Reynolds had published a paper predicting Io's volcanism based on tidal heating models shortly before Voyager's discovery. But the confirmation was nonetheless revolutionary. This discovery prompted scientists to reconsider other outer solar system bodies through the lens of potential tidal heating. When subsequent missions revealed evidence of subsurface oceans on Europa, Ganymede, Enceladus, and potentially other worlds, tidal heating provided a ready explanation for how these oceans could exist and persist so far from the Sun's warmth. The implications of tidal heating extend beyond the presence of liquid water to the chemical evolution of these ocean worlds. The heat drives geological activity, which in turn enables chemical reactions and material exchange between different layers. On Europa, for example, oxidants formed on the surface by radiation from Jupiter might be transported down through the ice shell to the ocean below, where they could react with reductants from the seafloor, creating chemical energy gradients that could potentially support life. Similarly, on Enceladus, tidal heating likely drives hydrothermal activity where the ocean meets the rocky core, as suggested by the detection of molecular hydrogen and silica nanoparticles in its plumes. These hydrothermal systems would leach minerals from the rocky interior into the ocean, creating a chemically rich environment with energy sources reminiscent of Earth's deep sea vents, where thriving ecosystems exist independent of sunlight. The varying intensities of tidal heating throughout these moons also create diverse potential habitats, each with its own chemical and physical characteristics. The interface between ice and water, water and rock, or between different ice phases, could each host unique conditions that might support different forms of life. The temperature gradients created by heat flowing from the interior outward provide energy sources for potential ecosystems. Beyond the ocean worlds we've discussed, tidal heating may play roles yet to be discovered elsewhere in the solar system. Neptune's moon Triton, with its nitrogen geysers and relatively young surface, shows signs of geological activity that might be driven by tidal forces, potentially indicating another subsurface ocean. The dwarf planet Haumea, with its elongated shape and rapid rotation, has experienced a complex tidal history related to the formation of its moons. Even some asteroids in multi-body systems might experience minor tidal heating. As we look to the future exploration of ocean worlds, understanding tidal heating will be crucial for interpreting what we observe. Missions like NASA's Europa Clipper and the European Space Agency's JUICE will study the Jovian moons in unprecedented detail, mapping their surface features, characterizing their magnetic fields, analyzing their compositions, and potentially detecting active processes like plumes or cryovolcanism. The data from these missions will refine our models of tidal heating and help us better understand how these hidden oceans are maintained. Future missions might carry ice-penetrating radar to map the thickness of ice shells and the depth of subsurface oceans. Seismometers placed on the surface could detect vibrations from tidal flexing and internal movements, providing direct evidence of ongoing tidal processes. Sample return missions, particularly from plumes like those of Enceladus, could allow detailed analysis of ocean materials, potentially revealing signatures of hydrothermal activity or even biological processes if they exist. The ultimate goal would be to access these subsurface oceans directly, perhaps through melting or drilling through the ice shell, or by sampling plumes that bring deep materials to the surface. Such missions present enormous technical challenges, but would provide unparalleled insights into these alien seas and their potential habitability. As we contemplate the ocean worlds of our solar system, warmed from within by the perpetual dance of orbital resonances and gravitational forces, we're reminded of the unexpected ways that familiar processes can create habitable environments in seemingly inhospitable places. What once seemed a cosmic coincidence, Earth's fortuitous position in the Sun's habitable zone now, appears as just one of many possible arrangements that could support liquid water and potentially life. Tidal heating teaches us that habitability extends beyond the traditional boundaries set by a star's warmth. It shows us that even in the dim outskirts of a planetary system, energy and liquid water can persist if the gravitational choreography aligns in certain ways. This realization dramatically expands the potential real estate for life, not just in our solar system but throughout the universe, where moons of giant exoplanets might harbor their own tidally heated oceans, awaiting discovery by future generations of astronomers and astrobiologists. When we think of oceans, our minds naturally drift to Earth's vast sea-azure expanses of salty water teeming with life. Their chemistry, a complex ballet of dissolved minerals, gases, and organic compounds shaped by billions of years of geological and biological processes. But what of the hidden oceans beyond our world? What strange chemistries might they harbor? And how might these alien compositions influence their potential as habitats for life? Unlike Earth's surface oceans, directly observable and easily sampled, the subsurface oceans of outer solar system bodies remain largely theoretical constructs. We infer their existence through indirect evidence, magnetic field interactions, surface features, gravitational measurements, but their specific chemical compositions remain educated guesses based on models, surface analyses, and the occasional fortuitous sampling of material ejected from below, as with the plumes of Enceladus. Yet these guesses are informed by a growing understanding of the physical and chemical processes that shape these distant worlds. Let's begin with perhaps the most basic question. What are these oceans made of? While water is the simple answer, the reality is far more complex. Pure water is rarely found in nature, and the oceans of these worlds surely contain a variety of dissolved compounds that dramatically alter their properties and potential as habitable environments. The evidence for salinity in these oceans comes from multiple sources. For Europa and Ganymede, the induced magnetic fields detected by the Galileo spacecraft require an electrically conductive layer below the surface, water being the most plausible explanation. For Enceladus, direct sampling of its plumes by the Cassini spacecraft revealed sodium and potassium salts, confirming that its ocean contains dissolved minerals. The specific salts likely vary between worlds. On Enceladus, analysis of its plume material suggests sodium chloride common table salt as a major component, along with sodium carbonate and possibly sodium bicarbonate. These alkaline salts suggest an ocean with a pH likely between 8 and 11, considerably more basic than Earth's oceans with their more neutral pH around 8.1. Europa's surface shows regions stained with reddish-brown material, particularly along fractures where subsurface material may have reached the surface. Spectroscopic analysis suggests these discolorations contain various sulfur compounds and salts altered by Jupiter's intense radiation. The presence of magnesium sulfate, Epsom sulfur, has been proposed, though more recent observations suggest sodium chloride might be the dominant salt, making Europa's ocean potentially more similar to Earth's oceans than previously thought. For Titan, the situation is more complex. Its subsurface water ocean likely contains significant amounts of ammonia, which acts as an antifreeze and allows the water to remain liquid at temperatures well below the normal freezing point. This ammonia-water mixture would create a chemical environment unlike any of Earth's natural waters, though perhaps slightly reminiscent of certain industrial cleaning solutions. The high pH resulting from dissolved ammonia would create an environment hostile to many Earth organisms, but potentially conducive to unique chemical reactions not common on our planet. Pluto and other distant dwarf planets might have even more exotic ocean compositions. Models suggest their oceans may contain ammonia, methanol, or other organic antifreeze compounds that depress the freezing point enough to maintain liquid water despite the extreme cold and limited internal heating of these small, distant worlds. Beyond these major components, the oceans likely contain a diverse array of minor constituents. Dissolved gases would vary based on each world's history and internal processes. Carbon dioxide might be common in many of these oceans, creating carbonic acid and influencing pH. Methane could be present, particularly in environments where it can form geologically through water-rock interactions. Hydrogen gas, a potential energy source for certain types of microorganisms, has been detected in Enceladus's plumes and might bubble up from the ocean floors of other worlds as well. Organic compounds, those containing carbon and hydrogen, often with oxygen, nitrogen, and other elements, add another layer of complexity. Cassini detected simple organic molecules in Enceladus's plumes, including various hydrocarbons and possibly complex macromolecular structures. For Titan, with its hydrocarbon-rich surface environment, organic compounds from the surface might potentially migrate into the subsurface ocean over geological timescales, creating a chemically rich solution. These dissolved compounds would not be evenly distributed throughout these alien oceans. As on Earth, concentration gradients would exist, influenced by sources and sinks for different chemicals. The interfaces between the ocean and other layers, the ice shell above and the rocky core below, would be zones of particularly interesting chemistry. At the ocean-rock interface, water-rock interactions would release minerals and gases into the ocean. If hydrothermal systems exist at these ocean floors, as evidence suggests for Enceladus, they would create localized environments of distinctive chemistry, with steep gradients in temperature, pH, and chemical composition over small distances. On Earth, such gradients around hydrothermal vents create energy sources that microorganisms can exploit, supporting entire ecosystems independent of sunlight. The ocean-ice interface would create a different set of chemical gradients. In some regions, the base of the ice shell might be partially melting, releasing fresh water and any compounds trapped in the ice. In other areas, new ice might be forming, excluding salts and concentrating them in the remaining liquid. The ice itself might contain channels of concentrated brine, similar to those observed in Earth's sea ice, providing microhabitats with chemistry distinct from the bulk ocean. For worlds exposed to intense radiation, like Europa in Jupiter's radiation belts, the surface ice undergoes radiolysis, the breaking apart of water and other molecules by energetic particles. This creates oxidants, highly reactive chemicals that could be transported down through the ice shell to the ocean below. These oxidants, if they reach the ocean, could react with reduced compounds coming from the ocean floor, creating chemical energy sources similar to those that power many Earth ecosystems. This potential coupling of surface oxidants with seafloor reductants is particularly intriguing for Europa. The oxidant formation at the surface has been compared to oxygen production on Earth, though through physical rather than biological processes. If these oxidants reach the ocean and react with hydrogen or other reduced compounds from the ocean floor, they could create a global energy cycle, reminiscent of Earth's but entirely abiotic in origin. Of course, such a cycle could also potentially support life if it ever emerged in these oceans. The pressure conditions in these subsurface oceans add another dimension to their chemistry. At the depths where these oceans likely exist, under kilometers of ice, pressures would be considerably higher than in most of Earth's oceans. High pressure affects chemical reactions, altering solubility, reaction rates, and even which reactions are energetically favorable. Certain compounds become more soluble under pressure, potentially enriching these deep oceans in gases and minerals that would escape from surface waters. For the deepest oceans, like those thought to exist within Ganymede or Titan, pressures might become extreme enough to create exotic high-pressure phases of ice at the ocean floor, despite temperatures above the normal freezing point of water. These ice phases have crystal structures and properties different from common ice, and could interact with the ocean water in unique ways, potentially creating habitats unlike anything known on Earth. The temperatures within these oceans, while cold by Earth standards, would vary both within and between worlds. Moons experiencing significant tidal heating, like Europa and Enceladus, might have relatively warm ocean floors, with temperatures potentially reaching 50 degrees Celsius or higher near hydrothermal systems. The bulk ocean water would be cooler, and temperatures would decrease approaching the ice shell, likely reaching 0 degrees Celsius or slightly lower at the ice-water interface, depending on pressure and salinity. For worlds with less internal heating, like Pluto, ocean temperatures would be lower throughout, maintained above freezing only by the antifreeze effect of ammonia or other compounds and the pressure of the overlying ice. These cold temperatures would slow chemical reaction rates compared to warmer environments, potentially affecting the timescales over which complex chemistry could evolve. The age of these oceans influences their chemistry as well. Oceans that have existed in more or less their current form for billions of years would have reached different chemical equilibria than younger or more frequently changing environments. Water-rock interactions over billions of years would leach more minerals from the rocky core, potentially creating more concentrated brines. Organic chemistry, if it occurs, would have had more time to generate complex compounds. For worlds with potentially cyclical periods of freezing and thawing, the chemistry might be more dynamic. Freezing concentrates salts and other solutes in the remaining liquid, while complete freezing could trap zones of concentrated brine within the ice. Subsequent thawing would release these trapped compounds, potentially creating periods of distinctive chemistry during transitions between mostly frozen and mostly liquid states. The redox state of these oceans, the balance between oxidizing and reducing conditions, is a crucial factor for potential habitability. Life on Earth exploits redox gradients, extracting energy from the controlled movement of electrons, from reduced compounds like hydrogen or methane to oxidizers like oxygen or sulfate. Without such gradients, the energy sources for life would be limited. For Europa, the surface oxidants and potential seafloor reductants could create a globally habitable redox gradient if transport mechanisms exist to bring these chemicals together. For Enceladus, the detection of molecular hydrogen in its plumes suggests ongoing water-rock reactions at its ocean floor, producing reductants that could fuel potential ecosystems if oxidants are available. For Titan, with its thick atmosphere shielding the surface from radiation, oxidant production might be limited, potentially creating a more reducing ocean environment. The organic chemistry possible in these oceans is perhaps the most speculative yet fascinating aspect of their potential. On Earth, liquid water provides the medium in which the complex chemistry of life occurs. The carbon-based molecules that form the structural and functional components of organisms' proteins, nucleic acids, lipids, carbohydrates are synthesized, maintained, and recycled within water environments, despite not being particularly soluble in water themselves. In the alien oceans of outer solar system worlds, different conditions might favor different types of organic chemistry. The presence of ammonia in Titan's ocean, for instance, creates an environment where certain organic reactions might proceed more readily than in pure water. Ammonia can act as a better solvent for many organic compounds and can participate directly in certain reactions. For worlds with significant organic material on their surfaces, like Titan with its hydrocarbon lakes, or the radiation-processed surfaces of Europa and Ganymede, mechanisms that transport this material to the subsurface ocean could provide chemical building blocks for further reactions. Impacts might melt through the ice shell temporarily, allowing surface material to mix with ocean water. Tectonics within the ice shell might subduct surface ice, carrying any embedded organic material with it. Or gradual diffusion through the ice might allow certain molecules to migrate between surface and ocean over geological timescales. The interfaces between different phases or environments often provide the most interesting chemistry. On Earth, the boundary between water and air, water and minerals, or water and organic phases creates zones where molecules can concentrate and react differently than in the bulk solution. In subsurface oceans, the water ice and water rock interfaces would serve similar roles, potentially concentrating certain compounds and catalyzing specific reactions. Clay minerals, likely present where ocean water interacts with rocky material, have properties particularly relevant for prebiotic chemistry. They can absorb organic molecules, concentrate them, and catalyze reactions between them. Some origin of life theories propose that clay surfaces played a crucial role in the emergence of biological molecules on early Earth. Similar processes might occur at the rocky ocean floors of worlds like Europa and Enceladus. The chemistry of these alien oceans also relates directly to their potential as habitats for life. Life as we know it requires certain specific chemical conditions: liquid water, a source of carbon, essential elements like nitrogen, phosphorus, and sulfur, and energy gradients that can be harnessed through electron transfer reactions. The evidence suggests that many subsurface oceans check these basic boxes, containing liquid water, carbon compounds, and potential energy sources. However, the availability of these essentials might vary widely between different ocean worlds and within specific regions of a single ocean. Phosphorus, a crucial element for Earth life used in DNA, RNA, ATP, and cell membranes, might be limiting in some of these environments if mechanisms to release it from rocky materials are insufficient. Nitrogen might be abundant in ammonia-rich oceans like Titan's, but potentially scarcer in others. Energy sources would be concentrated near interfaces like hydrothermal vents, rather than distributed evenly throughout the ocean volume. The chemistry of these oceans would not be static, but would evolve over time through various processes. Initial ocean formation, as a world heated and ice melted, would involve the preferential dissolution of more soluble compounds from the surrounding rock and ice. Ongoing geological processes would continue to add and remove chemical hydrothermal activity, releasing minerals and gases from below, freezing at the ice shell base, potentially removing fresh water and concentrating salts, and various transport mechanisms moving chemicals between different regions. If life emerged in any of these oceans, it would dramatically alter their chemistry, as it has on Earth. Biological processes selectively consume certain compounds and produce others, creating distinctive chemical signatures. The absence of such biological modification might be one of the most significant differences between Earth's oceans and lifeless extraterrestrial oceans, though detecting such differences through remote sensing remains enormously challenging. Our most direct chemical data from any subsurface ocean comes from Enceladus, whose plumes have been sampled directly by flying the Cassini spacecraft through them. Even this sampling, however, may not represent the ocean as a whole, as the plume material undergoes changes as it rises through cracks in the ice and expands into space. Nevertheless, the detection of salt, organic compounds, and molecular hydrogen in the plumes provides compelling evidence for a chemically rich, potentially habitable subsurface environment. Future missions may provide more detailed chemical profiles of these alien oceans. The Europa Clipper mission, scheduled to launch in 2024, will carry instruments capable of analyzing any plume material it might encounter during multiple flybys of Europa. The European Space Agency's JUICE mission will study Ganymede, Europa, and Callisto, potentially providing comparative data on their ocean compositions through surface spectroscopy and other remote sensing techniques. More ambitious future missions might include landers that could sample surface materials recently emerged from below, or even, eventually, probes that could penetrate the ice shell to sample the ocean directly. Each step will refine our understanding of these exotic chemical environments and their potential as habitats for life. As we contemplate the chemistry of these alien oceans, we're reminded of the diversity and adaptability of life on Earth, which has evolved to thrive in environments ranging from caustic hot springs to subglacial lakes to highly saline brines. The chemistries we're discovering on other worlds, while different from Earth's oceans in many ways, don't appear to be beyond the theoretical limits of habitability. Whether life actually exists in any of these distant seas remains unknown, but the chemical conditions for its possibility seem increasingly plausible as we learn more about these fascinating worlds. For centuries, our search for life beyond Earth focused on planetary surfaces, places where sunlight could power photosynthesis, where atmospheres could protect fragile organisms, where liquid water could flow openly under alien skies. But as we've discovered ocean worlds throughout our solar system, a profound shift has occurred in our thinking. Perhaps the most widespread habitats for extraterrestrial life aren't sun-drenched surfaces at all, but hidden realms beneath kilometers of ice, where sunlight never penetrates and where conditions have remained stable for billions of years. To assess the possibility of life in these subsurface oceans, we must first examine what makes an environment habitable. The basic requirements for life, as we know it, include liquid water as a solvent, essential chemical elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, sources of energy to power metabolism, and physical conditions: temperature, pressure, pH, salinity that allow complex organic molecules to form and persist. How do the subsurface oceans of outer solar system worlds measure up against these criteria? The first requirement, liquid water, is clearly met. The evidence for subsurface oceans on Europa, Enceladus, Ganymede, Titan, and potentially several other worlds is compelling, based on multiple independent lines of evidence, including magnetic field interactions, gravity measurements, surface features, and in Enceladus's case, direct sampling of ocean material in its plumes. These aren't small, isolated bodies of water, but global or near-global oceans, many containing more water than all of Earth's oceans combined. The essential chemical elements are likely present as well. Carbon, hydrogen, and oxygen are abundant throughout the solar system, forming the basis of water, carbon dioxide, methane, and various organic compounds. Nitrogen appears to be present in significant quantities in Titan's system and has been detected in Enceladus's plumes. Phosphorus and sulfur, while less directly observed, are common elements in rocky bodies and would likely be leached into the oceans through water-rock interactions at the ocean floor. Energy sources present a more interesting question. On Earth's surface, the vast majority of ecosystems rely ultimately on sunlight, with photosynthetic organisms capturing solar energy and converting it into chemical energy that flows through food webs. In the perpetual darkness of subsurface oceans, photosynthesis is impossible. Are there alternative energy sources sufficient to power potential ecosystems? The answer, surprisingly, is yes. On Earth, we've discovered thriving ecosystems completely independent of sunlight, most dramatically around hydrothermal vents on the deep sea floor. These ecosystems rely on chemosynthesis rather than photosynthesis, the extraction of energy from chemical reactions rather than light. Microorganisms harness the energy released when certain chemical compounds react, particularly when hydrogen, hydrogen sulfide, or methane is oxidized. The subsurface oceans of outer solar system worlds likely provide similar energy sources. Hydrothermal activity is strongly suspected at the seafloor of Enceladus, based on the detection of molecular hydrogen and silica nanoparticles in its plumes. These materials provide strong evidence for hot water reacting with rocks, producing hydrogen gas that could fuel microbial metabolism. Similar processes likely occur on Europa and potentially other ocean worlds. Another potential energy source comes from radiation at the surface. On worlds like Europa, which is bathed in Jupiter's intense radiation, water molecules in the surface ice are split apart, creating oxidant-shyly reactive chemical species that could be transported down through the ice shell to the ocean below. There, they could react with reductants like hydrogen coming from the sea floor, releasing energy that organisms could harness. This creates the intriguing possibility of a radiation-driven ecosystem, where Jupiter's energy indirectly powers a biosphere in Europa's dark ocean. The physical conditions in these oceans' temperature, pressure, pH, salinity show considerable variation between worlds but generally fall within ranges that life could potentially tolerate. Temperatures likely range from just above freezing near the ice shell to potentially 50 degrees Celsius or higher near hydrothermal systems, well within the range where terrestrial organisms thrive. Pressures, while high due to the overlying ice shell, are comparable to those in Earth's deep oceans, where numerous organisms live. The pH and salinity, while not precisely known, appear from indirect evidence to be within ranges where adaptations would be possible for life as we know it. Based on these fundamental criteria, several subsurface oceans in our solar system appear to meet the basic requirements for habitability, but habitability is not the same as being inhabited. To assess whether life might actually exist in these hidden oceans, we need to consider additional factors: how life might originate in such environments, how it might adapt to their specific challenges, and what forms it might take. The origin of life remains one of science's great unsolved mysteries, even for Earth, with multiple competing theories about how non-living chemical systems transition to living ones. Many theories involve surface environments like tidal pools, clay-rich settings, or alkaline hydrothermal vents, where chemicals can concentrate and energy from various sources is available. Could similar processes occur in subsurface oceans? Hydrothermal systems at ocean rock interfaces provide one plausible setting. The alkaline hydrothermal vents discovered on Earth, like the Lost City Field in the Atlantic Ocean, create chemical and pH gradients, concentrate minerals, and form tiny compartments in their porous structures. These conditions could potentially facilitate the complex chemistry needed for life to emerge. The evidence for similar hydrothermal systems on Enceladus, and likely on Europa and other ocean worlds, suggests that if life can originate in such settings, it would have had the opportunity to do so multiple times in our solar system. Another possibility is that life originated at the surface during an earlier period when conditions were different, and subsequently retreated to the subsurface as surface conditions became inhospitable. For a world like Europa, however, surface conditions have likely been hostile for most of its history due to Jupiter's radiation, making a subsurface origin more plausible. A third possibility is panspermiath transfer of life between worlds via meteorites or other mechanisms. If life originated on Earth or Mars early in solar system history, could it have been transported to the moons of the outer planets? While not impossible, the challenges of such a journey surviving the ejection from the origin planet, the vacuum and radiation of space, and the impact on the destination world make this scenario less likely than an independent origin. Assuming life could originate in subsurface oceans, what forms might it take, and how would it adapt to these environments? The most likely form would be microbial, similar to the single-celled organisms that dominate Earth's extreme environments. These microbes might exist as free-floating cells in the ocean water, as attached communities on the underside of the ice shell, or on the ocean floor, or as colonies within porous rocks or ice structures. On Earth, microorganisms have evolved remarkable adaptations to extreme conditions. Psychrophiles thrive in near-freezing temperatures, with specialized enzymes that function when ordinary proteins would become too rigid. Barophiles have adapted to the crushing pressures of the deepest ocean trenches, altering their cell membranes and proteins to remain functional under conditions that would destroy less specialized organisms. Halophiles flourish in highly saline environments, balancing the osmotic pressure with internal solutes. Organisms living in subsurface oceans would likely evolve similar specializations to their particular environment. The metabolic strategies of such life forms would depend on the available energy sources. Where hydrogen is available from water-rock reactions, as appears to be the case on Enceladus, hydrogenotrophic organisms might dominate, using hydrogen as an electron donor and compounds like carbon dioxide or sulfate as electron acceptors. Where organic compounds are available, heterotrophs might consume these materials, extracting energy through various fermentation or respiration pathways. The specific biochemical mechanisms would likely differ from those on Earth in their details, while potentially following similar overall patterns dictated by the laws of chemistry and thermodynamics. The structure of potential ecosystems in these oceans would depend on the distribution of energy and nutrients. Earth's deep-sea hydrothermal vents support remarkably diverse communities, with primary producers harnessing chemical energy, various consumers feeding on these producers, and decomposers recycling organic material. Similar food webs could potentially develop around hydrothermal systems in subsurface oceans, though with fewer trophic levels than in Earth's more complex ecosystems. Away from such concentrated energy sources, life might be sparser, perhaps limited to microorganisms surviving on the slow rain of organic material from above, or on low-level chemical energy available from water-rock interactions. The ocean-ice interface might support distinct communities, particularly if materials from the irradiated surface make their way down through the ice shell, providing chemical energy sources different from those at the seafloor. The time available for life to evolve in these oceans is substantial. Evidence suggests that the subsurface oceans of worlds like Europa have likely existed for much of the solar system's 4.5 billion-year history. On Earth, life appears to have emerged relatively quickly after conditions became suitable, within the first few 100 million years. If similar timescales apply elsewhere, life would have had ample time to originate and evolve in these stable subsurface environments. The isolation of these ocean worlds from each other means that if life exists in multiple subsurface oceans, each biosphere would have evolved independently after its origin, potentially taking divergent evolutionary paths. This could result in fundamentally different biochemistries, presenting one of the most exciting possibilities for comparative biology, the chance to study life that evolved independently, potentially providing insights into which aspects of life are universal consequences of chemistry and physics, and which are historical accidents specific to Earth's evolutionary path. Different ocean worlds would present different environmental conditions and thus different evolutionary pressures. Enceladus, with its relatively thin ice shell and active plumes, might have more material exchange between the surface and subsurface than Europa, with its thicker shell. Ganymede's ocean, potentially sandwiched between different ice layers, might have less interaction with rocky materials than oceans in direct contact with a rocky core. Titan's ammonia-rich ocean would present a distinct chemical environment from the others. Each world would thus potentially give rise to life with unique adaptations. On Earth, virtually all life shares certain fundamental features: DNA as the genetic material, RNA as the messenger, proteins as the functional molecules, lipid membranes as boundaries, and the same basic metabolic pathways with minor variations. This universal biochemistry strongly suggests a single origin for all terrestrial life. Finding life with a different biochemical basis, using perhaps different informational molecules or alternative metabolic pathways, would provide strong evidence for a second, independent origin of life. The plumes of Enceladus provide a unique opportunity to search for evidence of life in a subsurface ocean without having to drill through kilometers of ice. The Cassini spacecraft detected complex organic molecules in these plumes, though nothing that can be definitively identified as biological in origin. Future missions designed specifically to search for biosignatures could sample these plumes with more sensitive instruments, potentially detecting amino acids, fatty acids, or other biomolecules if they exist in the ocean below. For Europa, the evidence for occasional plumes is less consistent, but future missions like NASA's Europa Clipper will be equipped to detect and analyze any plume material they encounter. Additionally, radiation-processed material from the subsurface might be present on Europa's surface, particularly in recently resurfaced areas, providing another potential sampling opportunity without direct access to the ocean. More ambitious future missions might include landers that could sample the surface for evidence of biological material that has made its way up from below, or even, eventually, probes that could melt or drill through the ice shell to directly sample the ocean. Such missions present enormous technical challenges, but would provide definitive answers about the presence or absence of life. What would constitute convincing evidence for life in these subsurface oceans? The detection of certain organic compounds particularly those with structures or isotopic compositions characteristic of biological processes, would provide suggestive evidence. The presence of cell-like structures, especially if they contained complex organic molecules arranged in ways indicative of metabolism or reproduction, would provide stronger evidence. Genetic material analogous to DNA or RNA, capable of storing information and directing the synthesis of functional molecules, would be even more compelling. And ultimately, evidence of active metabolism, the ongoing chemical processes that sustain life, would provide the most definitive proof. The absence of such evidence wouldn't necessarily mean these oceans are lifeless. Life might be sparse or confined to specific regions like the seafloor, making it difficult to detect in limited samples. It might use biochemistry sufficiently different from Earth's that our search methods, based on terrestrial life, would miss it entirely. Or these oceans might indeed be sterile, despite being habitable, if the specific conditions needed for life to originate were never met, or if some unknown factor prevents life's emergence or survival. If life does exist in these subsurface oceans, it would have profound implications for our understanding of life's prevalence in the universe. Finding even microbial life on one world would suggest that life can originate relatively easily given the right conditions, making it potentially common throughout the galaxy. Finding life on multiple ocean worlds within our own solar system would strengthen this conclusion dramatically. And finding biochemically distinct life forms in different oceans would suggest that life's emergence follows multiple possible pathways, further increasing the probability of life elsewhere. Beyond these scientific implications, discovering extraterrestrial life would transform our philosophical and cultural perspectives. For thousands of years, humanity has questioned whether we are alone in the universe. Finding life, even microscopic life, beneath the ice of distant moons would provide the first definitive answer to this ancient question. As we contemplate these possibilities, it's worth noting that our own planet hosts analogues to the subsurface oceans of outer solar system worlds. Antarctica's subglacial lakes, buried beneath kilometers of ice, remain isolated from the surface for thousands to millions of years. Lake Vostok, the largest of these, has been isolated for potentially 15 million years, yet contains microbial life adapted to its dark, cold, high-pressure environment. Similarly, groundwater ecosystems deep within Earth's crust harbor microbial communities that never see sunlight, deriving energy from chemical reactions with the surrounding rocks. These terrestrial analogues provide insights into how life might adapt to subsurface ocean conditions, while also highlighting the remarkable adaptability of life on Earth. They serve as natural laboratories where scientists can study life in environments somewhat similar to those on ocean worlds, developing techniques that might eventually be applied to the exploration of those distant habitats. The search for life in subsurface oceans connects to broader questions about life's origins and distribution. If life originated independently on multiple worlds within our solar system, it suggests that life emerges readily when conditions permit. This would have profound implications for astrobiology and for our estimates of how common life might be throughout the galaxy. Subsurface oceans also expand our concept of the habitable zone, the region around a star where conditions might support life. Traditionally defined as the range of distances where a planet's surface temperature allows for liquid water, this concept becomes more complex when we consider worlds with internal heat sources that can maintain subsurface oceans regardless of their distance from the sun. The moons of gas giants, with their tidal heating, might harbor habitable environments even in otherwise frigid regions of a planetary system. This expanded habitability has implications for our search for life around other stars. Moons of giant exoplanets, even those orbiting outside their star's conventional habitable zone, might host subsurface oceans and potentially life. As our detection methods improve, allowing us to find and characterize exomoons, these worlds may become prime targets in our search for life beyond our solar system. As we await future missions that will further explore ocean worlds and perhaps directly sample their hidden seas, we can only speculate about what might dwell in those dark waters. Perhaps nothing sterile oceans of chemical potential never realized. Perhaps simple microorganisms, the universe's most common form of life, adapting to their cold, dark environment, much as they have to Earth's extreme habitats. Or perhaps something more complex and entirely alien, life that evolved along paths never taken on our world, revealing new possibilities for what life can be. Whatever we ultimately discover beneath the ice of distant moons, the search itself has already transformed our understanding of our solar system and the potential for life within it. What once seemed a nearly empty void, with Earth alone bearing the spark of life, now appears as a system potentially rich with hidden habitable environments. In extending our search for life from planetary surfaces to subsurface oceans, we've expanded not just where we look but what we imagine might be possible, a testament to both the creativity of science and the persistent human desire to understand our place in the cosmos. How do you investigate an ocean you cannot reach, let alone see? This question lies at the heart of one of planetary science's greatest challenges. The subsurface oceans of the outer solar system represent some of the most intriguing environments for scientific exploration and the search for extraterrestrial life. Yet they are hidden beneath kilometers of ice, hundreds of millions of kilometers from Earth. Our conventional methods of oceanography, ships, submarines, diverse are useless in these distant seas. Instead, scientists have developed a remarkable array of indirect methods to study these hidden oceans, along with ambitious plans for future exploration that might one day allow us direct access to these alien waters. The exploration of subsurface oceans began with inference, the educated guess that such oceans might exist based on theoretical models of how these moons formed and evolved. In the 1970s, planetary scientists speculated that tidal heating might keep the interiors of moons like Europa warm enough for liquid water to persist beneath their icy surfaces. These early speculations were largely theoretical, based on calculations of orbital dynamics and heat flow rather than direct observations. The Voyager missions in the late 1970s and early 1980s provided the first detailed images of the outer planet moons, revealing surface features on Europa in particular that suggested the presence of a subsurface ocean. The fractured, resurfaced terrain indicated an active ice shell, potentially floating on a liquid layer beneath. However, these observations remained suggestive rather than definitive. The Galileo mission, which orbited Jupiter from 1995 to 2003, provided the first compelling evidence for subsurface oceans through multiple independent measurements. Its magnetometer detected an induced magnetic field at Europa that changed as the Moon moved through Jupiter's magnetic field, precisely what would be expected if an electrically conductive layer of salt water existed beneath the lactid surface. Similar, though weaker, signatures were detected at Ganymede and Callisto. Galileo's cameras captured higher resolution images of Europa's surface features, including chaos terrain, where the ice appeared to have broken apart and refrozen, and double ridges that might form when water from below pushes up through fractures in the ice. These features strengthened the case for a subsurface ocean in active communication with the ice shell above it. The Cassini mission to the Saturn system, active from 2004 to 2017, made the most dramatic discovery in the exploration of subsurface oceans, the plumes of Enceladus. These visible jets of water vapor, ice particles, and other materials erupting from the Moon's south polar region provided direct samples of a subsurface ocean without the need to drill through ice. Analysis of this plume material by Cassini's instruments revealed salt, organic compounds, and molecular hydrogen, offering unprecedented insights into the chemistry of an alien ocean. Cassini also studied Titan extensively, using radar to penetrate its thick atmosphere and map its surface features, including its hydrocarbon lakes. While the evidence for Titan's subsurface water ocean comes primarily from models of its interior structure and measurements of its rotation, Cassini's comprehensive study of this complex world has informed our understanding of how its surface and subsurface environments might interact. The New Horizons mission, which flew past Pluto in 2015, revealed a world far more geologically active than expected, with regions showing relatively few impact craters, suggesting recent resurfacing. Combined with theoretical models of Pluto's internal structure and evolution, these observations suggest the possibility of a subsurface ocean, maintained by radioactive decay in its rocky core and the insulating properties of its ice shell. While these missions have provided remarkable insights, they've barely begun to answer our questions about these hidden oceans. Future missions planned for the coming decades will employ more sophisticated tools to probe these environments in greater detail. NASA's Europa Clipper mission, scheduled to launch in 2024, will conduct dozens of close flybys of Europa, using a suite of instruments specifically designed to characterize its subsurface ocean and assess its potential habitability. Its ice-penetrating radar will attempt to determine the thickness of the ice shell and potentially detect water pockets within it. Its magnetometer will make precise measurements of the induced magnetic field, providing information about the depth, salinity, and other properties of the ocean. And its surface mapping instruments will search for recently active regions where ocean material might have reached the surface, as well as plumes similar to those seen on Enceladus. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, scheduled to launch in 2023, will study Ganymede, Callisto, and Europa, with a particular focus on Ganymede, around which it will eventually enter orbit. Like Europa Clipper, it will carry ice-penetrating radar and other instruments to characterize these moons' subsurface oceans, allowing for comparative studies of these different watery worlds. NASA has also considered a lander mission to Europa that would follow the Clipper orbiter. Such a mission would place scientific instruments directly on Europa's surface, potentially including a seismometer to detect vibrations that could reveal details about the ice shell and ocean below, as well as sampling equipment to analyze surface materials for evidence of ocean-derived compounds. For Enceladus, various mission concepts have been proposed to follow up on Cassini's discoveries. These range from relatively simple flyby missions designed to sample its plumes with more sensitive instruments to ambitious concepts like the Enceladus Life Finder, which would orbit Saturn and make multiple passes through the plumes, or the even more audacious Enceladus Orbolander, which would first orbit the Moon and then land on its surface to study its environment over an extended period. These planned and proposed missions represent the next generation of exploration, building on the discoveries of previous missions with more focused objectives and more sophisticated instruments. But what about the more distant future? What technologies might eventually allow us to directly access and explore these subsurface oceans? The most straightforward approach conceptually, though enormously challenging technically, would be to land a probe on the surface that could melt through the ice shell to reach the ocean below. Various concepts for such cryobots or melt probes have been proposed and tested in terrestrial environments like Antarctica. These devices would carry their own heat source, potentially a small nuclear reactor for long-term power, and slowly melt their way downward through the ice. For Europa, with an estimated ice shell thickness of 15 to 25 kilometers, such a mission would be daunting but potentially feasible with future technology. The probe would need to carry not only a heat source, but also instruments to analyze the ocean once reached, and communications equipment to relay data back to the surface and ultimately to Earth. It might also deploy small submersibles to explore the ocean environment beyond the immediate vicinity of the melt hole. The challenges of such a mission are immense. The radiation environment around Europa would damage electronics, requiring substantial shielding. The power requirements for melting through kilometers of ice would necessitate an advanced, reliable power source. The communication system would need to transmit data through both the ocean water and the refrozen ice above. And the entire system would need to operate autonomously, given the communication delays between Earth and the outer solar system. For moons with thicker ice shells, like Ganymede or Titan, direct access to the subsurface ocean via melting becomes even more challenging. Alternative approaches might be needed, such as targeting regions where the ice shell is thought to be thinner, or where natural features like cryovolcanic vents might provide easier access to the ocean below. A different approach would be to focus on sampling materials from these oceans that reach the surface naturally, as with Enceladus's plumes. Future missions might collect plume material for more detailed analysis than Cassini could perform, potentially including searches for complex organic compounds, cell-like structures, or other potential biosignatures. Similar approaches could be applied to Europa if its putative plumes prove consistent enough for targeted sampling. Even without direct access to these oceans, there are numerous techniques that can provide information about their properties. Gravitational measurements can reveal details about a world's internal mass distribution, including the presence of a liquid layer. Libration-subtle wobbles in a moon's rotation can indicate whether the outer shell is decoupled from the interior by a liquid layer. Magnetic field measurements, as discussed earlier, can detect electrically conductive subsurface layers consistent with salty oceans. Ice-penetrating radar, which has been used effectively to study Earth's ice sheets and subglacial lakes, can potentially map the ice-ocean boundary and detect features within the ice shell. Different radar frequencies penetrate to different depths, allowing for comprehensive mapping of the shell structure. While the thick ice shells of outer solar system moons present challenges beyond those of Earth's ice sheets, the basic principles remain applicable. Seismic measurements detecting and analyzing vibrations traveling through a moon's structure would provide perhaps the most detailed information about subsurface oceans. On Earth, seismology has been crucial for understanding our planet's interior structure, revealing the boundaries between the crust, mantle, and core, as well as variations within these layers. Applied to ocean worlds, seismometers placed on the surface could detect natural vibrations from ice fracturing or tidal flexing, as well as artificial seismic waves created by impact devices or other sources. Analysis of how these waves travel through the moon would provide information about the thickness and properties of different layers, including the ice shell and ocean. Infrared and spectroscopic observations of surface materials can identify compounds that might originate from the ocean below. On Europa, for instance, regions discolored with reddish-brown material might contain salts or other ocean-derived chemicals altered by radiation after reaching the surface. Detailed analysis of these materials could provide insights into the ocean's chemistry without direct access. Beyond these specific techniques, the comparative study of different ocean worlds offers a powerful approach to understanding these environments. By examining similarities and differences between Europa, Enceladus, Ganymede, Titan, and potentially others, scientists can distinguish between universal processes that operate across all these worlds and unique features specific to individual moons. This comparative approach can provide insights that might not be apparent from studying any single world in isolation. The search for life in these hidden oceans presents additional challenges beyond simply characterizing their physical and chemical properties. Detecting life requires not just identifying potential habitats, but finding evidence of biological processes within them. Various biosignature detection methods have been proposed for future missions, ranging from relatively simple chemical analyses to more sophisticated approaches. Mass spectrometry, which identifies molecules based on their mass and charge, can detect complex organic compounds potentially indicative of life. Chromatography can separate complex mixtures of compounds for more detailed analysis. Microscopy might detect cell-like structures if present in samples. Electrochemical techniques could identify redox chemistry characteristic of biological processes, and various assays specific to Earth-like biochemistry could detect particular molecules like amino acids, nucleic acids, or lipids. The challenge with such approaches lies in distinguishing between biological and non-biological origins for any compounds or structures detected. On Earth, this distinction is often straightforward because we can compare unknown samples to known biological materials. In alien environments, where life might use different biochemistry, or where abiotic processes might produce compounds or structures resembling those of life, the distinction becomes far more difficult. This challenge motivates the development of agnostic biosignature detection methods approaches that can identify life based on universal characteristics rather than specific Earth-like biochemistry. Such methods might focus on patterns of complexity, evidence of energy utilization, or chemical distributions that deviate from what would be expected from purely abiotic processes. While still in their infancy, these techniques represent a promising direction for future life detection missions. The exploration of subsurface oceans connects to broader efforts in planetary protection, ensuring that our missions don't contaminate other worlds with Earth organisms, or conversely, expose Earth to potentially harmful extraterrestrial materials. For missions to ocean worlds, particularly those searching for life, these considerations take on special importance. Spacecraft must be thoroughly sterilized before launch to minimize the risk of transporting Earth microbes to potentially habitable environments. This is especially crucial for components that might directly contact a moon's surface or, in more ambitious future missions, its subsurface ocean. The standards for such sterilization are even more stringent than for missions to Mars, given the potentially more hospitable conditions in subsurface oceans. For sample return missions, which might eventually bring materials from these oceans back to Earth, protocols would be needed to ensure that any potentially harmful extraterrestrial organisms or compounds are contained and studied safely. While the risk is likely minimal, the potential consequences of uncontrolled exposure to alien biology necessitate careful planning and stringent safeguards. The remote nature of these ocean worlds creates additional challenges for exploration beyond those of the harsh environments themselves. The vast distances between Earth and the outer solar system make communication delayed and limited in bandwidth. A signal traveling at the speed of light takes between 33 minutes and 5.5 hours to reach the outer planets, depending on their positions in their orbits, making real-time control of spacecraft impossible. This necessitates a high degree of autonomy for any mission, with onboard systems capable of making decisions without input from Earth. Power generation presents another challenge in the outer solar system, where sunlight is too weak for efficient solar power. Most outer planet missions rely on radioisotope thermoelectric generators, which convert heat from the decay of radioactive material, typically plutonium-238, into electricity. Future missions, particularly those with high power requirements like melt probes, might need more advanced nuclear power systems, such as small fission reactors. Despite these challenges, the exploration of subsurface oceans represents one of the most exciting frontiers in planetary science and astrobiology. Each mission builds upon the discoveries of its predecessors, gradually piecing together our understanding of these hidden seas. The Galileo mission revealed the likely presence of Europa's ocean. Cassini directly sampled Enceladus's ocean through its plumes. Future missions will characterize these oceans in greater detail and search for signs of life within them. And perhaps someday, a probe will breach the ice shell of one of these worlds and send back the first images from an alien ocean, a momentous step in our exploration of the solar system and our search for life beyond Earth. As we develop and deploy these increasingly sophisticated methods of exploration, we're driven not just by scientific curiosity, but by some of humanity's most profound questions. Are we alone in the universe? How common is life? Can it exist in environments radically different from Earth's surface? The hidden oceans of the outer solar system may hold answers to these questions, if only we can develop the tools to properly ask them. Across the vast expanse of our solar system, hidden beneath crusts of ice on distant moons, alien oceans stir in perpetual darkness. They have never felt the kiss of sunlight. They have never known the rush of wind. They exist in isolation, separated from our familiar world by immense distances and impenetrable barriers. And yet, as we discover and study these hidden seas, they transform not just our understanding of our cosmic neighborhood, but our perception of ourselves and our home planet. The discovery of subsurface oceans throughout the solar system represents one of the most profound scientific revelations of our time, comparable in significance to the Copernican revolution that displaced Earth from the center of the universe, or the discovery of galaxies beyond our Milky Way that expanded our cosmic horizon. Like those earlier paradigm shifts, the recognition of widespread oceans beyond Earth forces us to reconsider long-held assumptions and opens new possibilities for how we understand our place in the cosmos. Perhaps the most immediate lesson these distant oceans teach us is that water, the liquid foundation of life, as we know it, is far more common in our solar system than once believed. For centuries, Earth was considered unique as the water planet, the only world where this precious substance existed in liquid form on the surface. Mars might have had ancient seas, long since lost to space or frozen beneath its dusty plains. Venus might have hosted primordial oceans before runaway greenhouse effects transformed it into a hellish furnace. But nowhere else, it seemed, could liquid water persist in substantial quantities. Now we know otherwise. Europa alone likely contains twice as much water as all of Earth's oceans combined. Hidden beneath its icy shell, Ganymede may harbor even more. In total, the subsurface oceans of the outer solar system represent a volume of liquid water many times greater than all of Earth's surface water. Rather than being rare and precious, water appears to be abundant in our cosmic neighborhood, sequestered not on planetary surfaces, but in the sheltered interiors of icy moons. This abundance challenges us to reconsider water's cosmic role. Rather than an exceptional substance unique to Earth's fortunate positioning in the Sun's habitable zone, water emerges as a common feature of planetary evolution, finding its equilibrium in different states, depending on local conditions. On Earth, those conditions allow it to exist as a surface ocean. On Europa and Enceladus, tidal heating and insulating ice shells permit liquid oceans despite the frigid external environment. On Mars and perhaps Ceres, it might persist in limited liquid form deep underground. In the Kuiper Belt and Oort cloud, it exists primarily as ice, but may occasionally melt during periods of heightened internal heating or external influences. Water, it seems, finds a way adapting to diverse cosmic environments through its unique physical properties, its ability to exist in multiple states, and its role as a nearly universal solvent. This ubiquity expands our conception of where habitable environments might exist, not just in our solar system, but throughout the galaxy. If liquid water can persist so far from our Sun, might it not also exist in the dark places of countless other star systems? The moons of distant gas giants, the subsurface regions of ice-covered world-soil, become potential abodes for life in this expanded view. Beyond the abundance of water itself, these hidden oceans teach us about water's resilience and persistence. Earth's surface oceans are relatively exposed, vulnerable to cosmic impacts, solar flares, and the vagaries of climate change. They have endured over geological time, but have also undergone dramatic transformations, from global freezes to periods of extreme warmth, from acidification events to changes in circulation patterns. The subsurface oceans of outer solar system moons, by contrast, exist in remarkably stable environments. Protected by kilometers of ice from external disturbances, isolated from atmospheric changes and solar radiation, they may have persisted in roughly their current form for billions of years. On Europa and Enceladus, tidal heating provides a steady, reliable energy source, while the overlying ice serves as an insulating blanket, trapping this heat within. The result is an environment that may have remained habitable for longer than any single environment on Earth's more dynamic surface. This stability offers a counterpoint to our understanding of habitability, which is often focused on Earth-like surface conditions. Perhaps complex life requires the dynamic environment of a planetary surface, with its cycles of day and night, its seasons, its changing atmospheric composition, and its exposure to cosmic radiation that might drive evolutionary adaptation. Or perhaps the steady state of a subsurface ocean provides a different kind of advantageous, consistent environment where life, once established, can persist without facing the extinction-level disruptions that have repeatedly altered Earth's evolutionary trajectory. If life exists in these hidden oceans, it would suggest that biology can emerge and thrive in environments far more limited and constrained than Earth's surface. This would challenge us to broaden our definition of habitability beyond the traditional focus on planets with atmospheres, exposed to starlight, within the narrow temperature range where surface water remains liquid. It would suggest that life is more adaptable, more resilient, and potentially more widespread than our Earth-centric perspective has led us to believe. The study of these ocean worlds also reveals how interconnected Earth's systems are compared to these more isolated environments. On our planet, the atmosphere, oceans, crust, and biosphere exist in dynamic equilibrium, each influencing the others through complex feedback loops. Carbon cycles between air, water, rock, and living organisms. Water evaporates from oceans, precipitates over land, and returns to the sea in river networks. Energy flows from sunlight to plants to animals and back to the environment. On ocean worlds like Europa, by contrast, the subsurface ocean exists in relative isolation. There may be some material exchange with the surface through cracks in the ice shell, and with the rocky core through water-rock interactions at the sea floor. But compared to Earth's interconnected systems, these exchanges are likely limited and occur over longer timescales. This isolation creates a fundamentally different type of environment tone, where change happens more slowly, where resources must be recycled more efficiently, and where energy flows along fewer pathways. Understanding these differences helps us appreciate the unique nature of Earth's integrated systems. Our planet's habitability depends not just on the presence of water, energy, and essential elements, but on the complex interactions between different spherous interactions that disperse resources, provide multiple habitats, and create redundancies that enhance resilience. The isolated oceans of outer solar system moons lack this interconnectedness, potentially limiting their habitability even while providing greater stability. These hidden oceans also challenge our perception of where in the cosmos the majority of habitable volume might exist. Earth's biosphere is primarily a surface phenomenon, with life concentrated in a relatively thin layer where land meets air or where sunlight penetrates ocean waters. Even the deep biosphere, extending kilometers into the crust and ocean floor, represents a small fraction of Earth's volume. In the outer solar system, by contrast, the potentially habitable environments of subsurface oceans encompass a much larger proportion of these moons' total volumes. Europa's ocean may be 100 kilometers deep beneath a relatively thin ice shell. Ganymede's might extend even deeper. These are not thin veneers of habitability, but substantial fractions of these worlds' entire structures. If we expand our view to the galaxy as a whole, this pattern might hold truth. Majority of habitable volume might exist not on planetary surfaces, but in subsurface oceans of ice-covered moons. If life can indeed thrive in such environments, it suggests that the majority of living biomass in the universe might exist in hidden, isolated pockets, rather than on exposed planetary surfaces, bathed in starlight. This would represent a profound shift in our cosmic perspective, akin to realizing that the visible stars represent only a tiny fraction of the universe's total mass. The comparison between Earth's oceans and these alien seas extends to their chemical compositions as well. Earth's oceans derive their particular chemistry from a complex history, the initial waters released from the planet's interior during and after formation, modified by interactions with the atmosphere, continental crust, and biosphere over billions of years. The result is a solution dominated by sodium and chloride ions, with dozens of other elements in smaller concentrations, many of them actively cycled by biological processes. The oceans of Europa, Enceladus, and other moons likely have their own distinct chemical signatures, shaped by different histories and ongoing processes. Evidence from Enceladus's plumes suggests an alkaline ocean rich in sodium, carbonate, and chloride, with a composition influenced by water-rock reactions at its seafloor. Europa's ocean chemistry remains less directly observed, but surface materials suggest salts, including magnesium sulfate and sodium chloride, potentially leached from its rocky core. These chemical differences reflect the unique geological contexts of these worlds, the specific rocks that water interacts with, the pressure and temperature conditions of these interactions, and the presence or absence of additional processes like surface-ocean exchange. Comparing these different oceanic chemistries helps us understand how geological context shapes aqueous environments, providing insights that can be applied to Earth's own oceanic history and future. If life exists in these alien oceans, it would have evolved to thrive in their particular chemical conditions, just as Earth's marine organisms are adapted to our ocean's specific chemistry. This raises the tantalizing possibility of comparative biochemistry, the study of how life adapts to different chemical environments, and whether certain chemical foundations are universal or contingent. Do all living systems use carbon as their structural backbone? Do they all employ water as their solvent? Do they all store information in nucleic acid-like molecules? The answers could reveal fundamental principles about life's chemical requirements and adaptability. The hidden nature of these oceans also prompts reflection on our own historical relationship with Earth's seas. For much of human history, the deep ocean remained as mysterious and inaccessible as Europa's subsurface waters are today. Ancient mariners ventured across ocean surfaces, but had little concept of what lay beneath. Myths and legends populated the depths with sea monsters and drowned civilizations. Even into the early modern period, the ocean floor remained largely unknown, its contours unmapped, its ecosystems unimagined. Only in the 20th century did technological advances, sonar, deep-sea submersibles, remotely operated vehicles begin to lift this veil of ignorance. The discovery of hydrothermal vents in 1977 revealed entire ecosystems thriving without sunlight, challenging fundamental assumptions about life's requirements. Ongoing exploration continues to discover new species and habitats in Earth's deep oceans, even as we peer across space toward the hidden seas of distant moons. This parallel between historical oceanic exploration on Earth and contemporary exploration of outer solar system oceans highlights recurring patterns in human discovery. We first observe the superficial features of distant realms, then gradually develop tools and methods to probe deeper. often discovering that our initial conceptions were limited or mistaken. The process humbles us, revealing the vastness of what remains unknown even in seemingly familiar territories. The technological challenges of exploring subsurface oceans beyond Earth echo those faced by deep-sea researchers, but at a far greater level of difficulty. Both endeavors require remotely operated or autonomous vehicles designed to withstand extreme pressures, operate in lightless environments, and communicate data back to human researchers. Both must overcome the fundamental challenge of physical distance in Earth's oceans, the combined physical and temporal distance in outer solar system exploration. These parallels create opportunities for technological cross-pollination. Advances in autonomous underwater vehicles for Earth's oceans inform designs for future submersibles that might explore Europa's waters. Techniques for sampling and analyzing extreme environments on Earth provide testbeds for instruments destined for outer solar system missions. Conversely, the extreme challenges of distant ocean exploration drive innovations that may later benefit Earth-based research. Beyond their scientific importance, these hidden oceans resonate with human imagination and mythology. Water has featured prominently in creation myths across cultures, from the primordial oceans of Genesis to the cosmic waters of Hindu cosmology. Many traditions speak of waters beneath the earth, or primordial abysses from which life emerged. While these myths arose from observation of terrestrial waters rather than knowledge of distant moons, they reflect recurring human fascination with water as a source of life and mystery. Science fiction has long imagined life in the oceans of other worlds, from Arthur C. Clarke's monolith builders beneath Europa's ice in 2010, Odyssey 2, to the aquatic civilizations of countless other stories. These imaginative explorations reflect both scientific speculation and deeper human connections to water as a symbol of the unknown, the nurturing, and the mysterious. As scientific knowledge of these worlds increases, it both constrains and inspires new fictional depictions, creating a dialogue between scientific discovery and imaginative exploration. This intersection of science and imagination highlights one of the most profound lessons these distant oceans teach us: that reality often exceeds our speculative visions. Few scientists in the mid-20th century would have predicted plumes of organic-rich water erupting from a tiny moon of Saturn. Fewer still would have imagined that a dwarf planet beyond Neptune might harbor a liquid water ocean beneath its glacial nitrogen plains. The solar system has revealed itself to be far more dynamic, complex, and potentially life-friendly than earlier generations of astronomers envisioned. This pattern of reality surpassing imagination gives us reason for humility about our current understanding. What other wonders might await discovery? What fundamental processes have we overlooked or misunderstood? The hidden oceans remind us that our knowledge remains incomplete, our exploration of even our own cosmic neighborhood still in its early stages. They encourage continued curiosity, open-mindedness, and investment in the tools and missions that expand our understanding. Perhaps the most profound lesson these ocean worlds offer relates to life itself. For centuries, Earth's status as the only known harbor of life has fed two contradictory tendencies in human thought: a sense of Earth's cosmic uniqueness and specialness, and a loneliness that yearns for companions in the cosmic vastness. The discovery that several worlds in our solar system possess what appear to be the basic ingredients for life: liquid water, energy sources, essential elements, stable conditions over geological timescales changes the contextual framework for both tendencies. If life exists in the subsurface oceans of Europa, Enceladus, or other worlds, it would demonstrate that biology can emerge independently in multiple environments, suggesting that life might be a common outcome of natural processes rather than an exceptional fluke. This would diminish Earth's uniqueness in one sense, while simultaneously connecting us to a broader cosmic community of living worlds. If, on the other hand, these apparently habitable oceans prove to be sterile, it would highlight the possibility that life's emergence requires additional factors beyond those we currently recognize. Perhaps specific chemical contexts, precise timing of events, or particular combinations of conditions are necessary. This would emphasize Earth's specialness while deepening the mystery of our origins. Either outcome would transform our perspective on humanity's place in the cosmos. The presence of even microbial life elsewhere in our solar system would forever change our self-conception as Earth's unique inhabitants, connecting us to a broader category of living worlds. The confirmed absence of life in seemingly habitable environments would sharpen questions about our origins and the conditions that enabled Earth's biological flourishing. As we await discoveries that might answer these profound questions, the ocean worlds already teach us to expand our thinking beyond terrestrial paradigms. They remind us that habitability takes diverse forms, that liquid water finds niches in seemingly inhospitable settings, and that energy flows through planetary systems in ways more varied than we once imagined. They challenge Earth-centric assumptions, while simultaneously deepening our appreciation for our homeworld's integrated systems that have nurtured complex life. The oceans beneath distant icy shells also provide perspective on humanity's environmental challenges. Earth's oceans face mounting pressures from climate change, acidification, pollution, and resource extraction. Understanding oceans as precious and potentially rare habitats in the cosmic context, even if more common than once thought, still far from ubiquitous, reinforces the imperative to protect and preserve our own. Simultaneously, the resilience of water in finding equilibrium across diverse planetary environments offers a metaphor for adaptation and perseverance. If water can persist in liquid form in the dark recesses of distant moons, maintained by the subtle interplay of internal heat and external pressure, perhaps Earth's systems too possess resiliences we haven't fully appreciated. This doesn't justify complacency about environmental damage, but might inform approaches to protection and restoration. As our exploration of these hidden oceans continues in coming decades, each new discovery will refine and expand these lessons. The Europa Clipper and JUICE missions will provide unprecedented, detailed views of the Jovian ocean moons. Future missions might sample Enceladus's plumes, with instruments designed specifically to detect signatures of life. Eventually, probes might penetrate the ice shells to directly explore these alien seas. Whatever we discover in these distant waters, the knowledge will inevitably reflect back upon ourselves, our origins, our place in the cosmos, our relationship with our own planet's oceans, and our potential futures as an exploring species. The hidden oceans, even as they remain physically beyond our reach, have already touched human consciousness, expanding our conception of where life might take hold and how diverse habitable environments might be. In the final analysis, what these oceans teach us is a lesson about perspective, about the limitations of Earth-centered thinking, and the expansiveness of cosmic possibilities. They remind us that our familiar world, with its sunlit seas and windswept shores, represents just one expression of how water shapes planetary environments. Beyond our atmospheric bubble, in the cold reaches of the outer solar system, different forms of oceanic existence unfold, dark, isolated, alien, yet connected to our own through the universal properties of water, rock, and energy that shape worlds throughout the cosmos. These lessons ripple outward from our solar system to inform our understanding of the galaxy beyond. As we detect exoplanets in growing numbers and begin to characterize their properties, the ocean worlds in our cosmic backyard remind us to look beyond Earth analogues in our search for potentially habitable environments. Moons of distant gas giants, subsurface regions of ice-covered worlds, the potential habitats for life expand beyond traditional conceptions, suggesting that the universe might be far wetter and potentially more life-friendly than we once imagined. Across the vast, cold reaches of our solar system, far from Earth's warm shores, oceans wait in darkness. They have never seen the light of stars. They have never felt the touch of gentle rain. They exist beneath crusts of ancient ice, hidden from our eyes, but not from our understanding. These are the secret seas of distant moons, the liquid hearts of worlds we once thought frozen throughout. As we drift towards sleep, let us contemplate these waters and the wonders they contain. Europa's vast ocean, twice the volume of all Earth's seas combined, churning beneath a cracked shell of ice that records the moon's history in its intricate patterns. Enceladus with its south polar geysers, spraying ocean samples into space as if reaching out across the void to announce, here too is water, here too might be life. Ganymede's deep ocean, perhaps layered between exotic forms of ice, unknown on our home world. Titan with its strange duality, methane lakes on the surface, a water ocean far below, two liquid worlds on a single moon. And distant Pluto, once considered the very definition of a cold, dead world, possibly harboring its own hidden sea, kept liquid by heat from within, and antifreeze compounds dissolved in its waters. These oceans challenge our perception of where life might find a foothold. We once limited our search to the narrow band around stars where surface water could remain liquid, the so-called habitable zone that Earth occupies around our Sunday. But these hidden oceans exist far beyond that zone, maintained not by the distant sun's feeble warmth, but by the subtle interplay of gravitational forces, internal heat, and insulating ice. They teach us that habitability extends further than we had imagined, taking shelter in unexpected places. If these oceans harbor life and we do not yet know if they do, it would transform our understanding of biology's cosmic prevalence. Life arising independently in multiple places within our solar system would suggest it emerges readily given the right conditions, making it potentially common throughout our galaxy and beyond. Finding even microbial organisms in Europa's waters, or Enceladus's plumes, would forever change our perception of our place in the universe, connecting us to a broader community of living worlds, while simultaneously highlighting the apparent uniqueness of Earth's complex biosphere. Even if these distant seas prove lifeless, they remind us of water's remarkable persistence and adaptability. This simple molecule, two atoms of hydrogen bound to one of oxygen, exists in liquid form from the scorching depths of Earth's ocean trenches to the frigid subsurface of Pluto. It finds equilibrium in diverse environments, shaped by local conditions, yet retaining its essential nature as the universal solvent, the medium in which chemistry becomes complex enough to potentially support biology. The waters that wait beneath these icy crusts have likely done so for billions of years. While Earth's surface has transformed repeatedly, continents drifting, mountains rising and eroding, climates warming and cooling, these isolated oceans may have remained relatively constant, providing stability rarely found on more dynamic worlds. If life exists there, it has evolved in environments far more consistent than any on Earth's surface, potentially taking different evolutionary paths than those followed by terrestrial organisms. As you drift towards sleep, imagine descending through the ice shell of Europa, passing through kilometers of increasingly warm ice until breaching into the vast, dark ocean below. No sunlight penetrates here, just the faint glow of possible hydrothermal vents and the subtle luminescence of organisms adapted to eternal darkness, if any exist. The pressure increases with depth, the water salty enough to remain liquid below normal freezing temperatures. Currents move slowly, driven by the moon's internal heat and the gravitational pull of massive Jupiter overhead. Or picture Enceladus, where the seafloor likely features hydrothermal systems venting warm, mineral-rich water into the surrounding ocean. These vents might resemble the black smokers of Earth's deep oceans, creating islands of warmth and chemical energy in an otherwise cold environment. If life exists here, it might cluster around these energy sources, just as Earth's deep-sea organisms congregate around our planet's hydrothermal systems, creating oases of biological activity. Consider Titan, where the subsurface water ocean contains significant amounts of ammonia, creating a chemical environment unlike any natural waters on Earth. This alien ocean exists isolated from the equally exotic surface environment, where rivers of liquid methane carve channels through ice ridges, flowing into hydrocarbon seas that reflect the orange haze of the nitrogen-rich atmosphere above. Two liquid worlds on one moon, each with its own unique chemistry, separated by a barrier of ice, yet potentially connected through cryovolcanic features that might occasionally allow materials to flow between them. Even as we explore distant worlds, Earth's own oceans remain partially mysterious to us. The deepest trenches have been visited by only a handful of crewed vessels. New species are regularly discovered in the abyssal depths, and the dynamic interactions between oceans, atmosphere, land, and biosphere continue to reveal their complexity as we study them. Our home planet's waters provide both contrast and connection to the alien oceans beyond, different in their surface exposure and solar warming. yet similar in their fundamental chemistry and potential for harboring life. The ocean worlds of our solar system exist in a state of waiting for our robotic emissaries to reveal more of their secrets, waiting perhaps for direct sampling of their waters by future missions, waiting possibly for the detection of biological signatures if life dwells within them. But they do not wait for purpose or meaning. They simply exist, their waters flowing in darkness, their chemistry unfolding according to the same physical laws that govern all matter throughout the cosmos. If they harbor life, that life exists not for our discovery, but for its own being, following its own evolutionary journey, in isolation from the terrestrial drama that produced our species. As humans, we bring meaning to our exploration, seeking connections between our world and others, between our life and possible life elsewhere. This search reflects our nature as conscious beings, pattern seekers who construct narratives to make sense of our place in the vastness. The ocean worlds, whether lifeless or teeming with alien microbes, exist independently of these narratives, while simultaneously informing them, challenging us to expand our thinking beyond terrestrial paradigms. Sleep now, with these waters in your mind, waters that exist as surely as those in Earth's oceans, though separated from us by unimaginable distance and barriers of ice. Sleep knowing that our solar system is far wetter than once believed, that liquid water persists in the cold outer reaches where conventional wisdom said it could not, that the potential abodes for life extend beyond the narrow zone, where planets like ours orbit stars like our Sunday. Let these hidden oceans enter your dreams, these dark waters untouched by light, yet warmed from within. They remind us that even in the coldest places, warmth can survive if properly sheltered. They teach us that liquid water, and potentially life itself, finds ways to persist in environments we once thought hostile to both. They show us that our solar system, and by extension our galaxy and universe, contain more possibilities, more potential habitats, more wonders than our Earth-centered perspective initially recognized. As consciousness fades and sleep approaches, carry with you the vastness of these oceans, the patience of water that has flowed in darkness for billions of years, the possibility of life evolving in isolation from our own biological history. These waters wait, as they have waited since the solar system's youth, neither expecting nor requiring our awareness of them, yet enriching our understanding when we turned our attention their way. The oceans beneath the ice teach us humility before the complexity and diversity of our cosmic neighborhood. They remind us that exploration reveals not just new places but new paradigms, not just unfamiliar environments, but unimagined possibilities. They exemplify nature's tendency to exceed our expectations, to implement solutions more varied than our limited imagination might conceive, to find equilibrium in conditions we might have dismissed as inhospitable. And if sleep still eludes you, ponder one final thought. Somewhere in our solar system right now, ocean currents are flowing in eternal darkness. Water is interacting with rock to release minerals and gases. Thermal gradients are creating convection patterns that have persisted for eons. These processes unfold whether we observe them or not, whether we understand them or not. But in reaching toward comprehension, in extending our awareness beyond our immediate environment to these distant seas, we participate in one of humanity's most noble endeavors, the expansion of knowledge beyond the boundaries of our direct experience, the connection of our minds to realities far removed from our everyday existence. Sleep now, under skies filled with stars and planets and moons, some harboring their own hidden oceans. Sleep with the awareness that water, the matrix of life on Earth, exists in abundance throughout our solar system, waiting in darkness, flowing in silence, perhaps nurturing life forms that have never known light, never felt wind, never imagined creatures like ourselves, contemplating their existence from an unimaginable distance. Sleep, and perhaps dream of what wonders wait to be discovered in the waters of worlds beyond our own.